Hello everyone, welcome back to Ask a Scientist Gaming, where we combine mediocre gameplay with expert science. I'm Ken Hansen. I'm a light and color chemist, which means I care about the color of molecules, what molecular properties dictate their color, and how they absorb light and what they do with that light energy, and try to do something useful with that light energy, like move electrons or make and break bonds for catalysis, for solar energy conversion, whatever it may be. But more importantly, joining me today is Dr. Sachin Shanbhag. Sachin, if you wouldn't mind introducing yourself.
Hi, Ken. Thank you for having me. Depending upon who I'm talking to, I am a computational material scientist or a polymer rheologist. And I'll tell you what both of them mean. So like other computational material scientists, I study materials, but instead of doing experiments in the lab, I try and study their properties by solving equations on a computer. I also think of myself, I mean, the other hat I wear, I think of myself as a polymer rheologist. Polymers are just long molecules. They're everywhere. They make up proteins and nucleic acids, which make you up. But they also, as you very well know, make up things like, polyethylene. I mean, look around you. There's just polymer everywhere.
Video games.
Yeah,
Exactly.
And rheology is the study of how materials respond to deformation. And polymers, when they're processed, exhibit some really interesting behavior, and studying how they respond to strain is not just a scientifically interesting question, but also an important engineering problem.
What do you typically teach? What are you teaching right now?
So this semester, I just got off teaching what we call as baby algorithms, or algorithms 1. So really just how to do what you may have learned in like 12th grade algebra or first year calculus, but just doing that on a computer. So how to do stuff like differentiation and integration and solving equations, etc. But just doing that on a computer.
I see. So
it's a fun class.
Semi-programming plus.
Oh, it's like an applied math type class. So so you have to program.
Very cool.
Right.
Equally important, what game are we starting with?
Oh, so we are going to do Big Bumpin.
Let's dive right in.
All right.
So you're going to pick another one?
All right. Let's just do that.
All right, some of you might recognize this game. This is the game we go to for default when a guest says, I don't care what I play, you can pick for me. Well, I picked Big Bumpin, the Burger King game. And so Sachin was last on. I looked this up. So you were one of our earliest guests. You were the 17th guest on stream, and it was July 21st, 2021.
Okay.
So it's been almost 3 years since you've been on the stream. Last time you played Dynamite Dan on the ZX Spectrum.
Yep.
One of the classic gaming systems. ZX. All right,
it's a British.
That's fair. Yeah. The ZX system. And this time you were like, I don't care what I play. Let's try something new. And so my default answer anytime a guest wants to play a random game is to bring out this one, which is it's called Big Bumpin. Ouch. Start. And so in 2004, Burger King, they had a really spectacular website where they had like viral videos, and they had something called Subservient Chicken where you type in codes and it would execute the actions. And it was really like they were early in the viral marketing game. And part of that website, they wanted to add a couple of games. And so they had 3 games, Big Bumpin', Sneak King, and then it was like a Pocket Racer game. And it turns out the people that played the game thought it was way too good just to be on a website. So what they did is they partnered with Xbox and said, we're going to release these on the Xbox. You can go to Burger King and pay like $4 and get an Xbox game. and this is the byproduct of that. So one of them is Big Bumpin', which is this, which are essentially a bumper car, and you're playing different bumper car related games. In this case, it's a hockey game. Other ones, it's survival mode. And Sachin is going to journey through all these. And no, he has never seen or heard of this game until about 20 minutes ago.
I'm telling Ken, you shouldn't expect me to improve over the course of the evening, because, I don't know. People talk about mind-body connection. I think I have a mind-body disconnection.
Don't worry, alcohol is it's a enhancing drug.
That's right.
It'll help.
So what did you teach this semester?
This semester, group theory and inorganic spectroscopy.
Oh wow!
So yeah,
is that
That's graduate level.
Yeah.
Yep. So 9 students in it, but it was like using symmetry to describe orbitals and overlaps and vibrational modes and things like that.
Oh, cool. So like one big thing that has, I mean, it's been happening since I think the last year, but definitely this semester, like this Chat GPT and other stuff. Did that, like, how did you negotiate that?
So I did not incorporate that in my classes at all.
Okay.
It's interesting you mentioned that. I have a paper under review right now. Oh, before that, Contra Crostix, welcome to the stream. Sneak King was so awful. Good day, streamers. Thank you for joining us. Thank you for the first time chat. If you're not clicking follow, click the follow, because you will get mediocre gameplay every time we stream. Sachin is delivering. Well, we're going to have fun while doing it. So, Contra, welcome to the stream. Thank you for joining us. But yeah, ChatGPT has been an interesting experiment for me because, I've been doing a bunch of test analysis, so you can do like Roche modeling and multiple choice exam outcomes and things like that. And I've done published a few papers on that, just like improving exams and comparing in-person versus online exams. But one of the things that was brought up when we compared the in-person to online, and it was because COVID induced it, is all the data I collected was pre-ChatGPT. And so the question was, what would ChatGPT look like on a multiple choice exam? And so we have a paper under review right now that basically uses...
So ChatGPT is taking the question or setting the exam?
No. Like taking it, I fed my test into ChatGPT and I wanted to see how it would answer the questions. And it doesn't perform great. It's like an average student or something like that.
And tell you, this was what level was this?
ChatGPT 3.5.
Gen Chem.
Gen Chem 2.
You would expect it to do reasonably well, right?
It's okay. It's an average student. But what's interesting is it gets like easy questions wrong and hard questions right. It doesn't behave like a student
That's
does.
right.
And so we can actually use that statistical behavior to see ChatGPT take a Gen Chem exam. So if you give me a Gen Chem answer key of multiple choice questions, I can tell you through this whether it was taken by a student or ChatGPT. Which is kind of fun.
That's interesting. So what's the type of a question that it gets wrong?
It's all over the place. There's hard ones that it gets right, and it gets it right for the wrong reason, or it like brute forces it. Like for us, you would say, okay, what's the boiling point from a phase diagram? Right? Well, ChatGPT doesn't need to have the diagram. It can just like look in the CRC manual and find the boiling point. Right. So it gets things right for the wrong reasons. And it's mechanistically very weird.
No, I remember like early on, I don't know what it is now. I mean, now there are so many of these models and so many different versions. It's hard to know. And also, like depending upon the time of the day and what machine because there's some stochasticity to the answer generated. So I don't know whether it takes the same test multiple times, whether the averages are stable or whether...
So it was plus or minus 5%.
Oh, that's pretty tight.
We fed it into the test. We fed it into ChatGPT 20 times just to see what the consistency was. And it's crazy. Like there are some questions that it gets right every single time. There's questions that get right 30% of the time and 20%, and some it gets wrong every single time. And so it's that's good though. You survived the last two. So yeah, this game type that Sachin's playing is survival mode. But yeah, it was a fun experiment just to see. And so what we're doing now, actually, my students are involved in this project, is one of the questions is what does it get wrong and why? And so what we have now is we have 5 semesters of exams, 930 questions. And what we're doing is making this giant spreadsheet that classifies the questions. So like, does it have an equation? Does it have a formula? Does it have a reaction? But also, where does it fall in Bloom's taxonomy? Is it conceptual? Is it factual? Blah, blah, blah.
And these questions are not just multiple choice questions.
They are multiple choice.
They're all multiple choice questions.
All multiple choice.
And do you require an explanation or just pick the right answer?
Choice. That's it. And we just give a lot of questions. So like it's a statistical warfare basically. But what we're going to do is apply machine learning and just see, is there a behavioral pattern? Is there something ChatGPT is good at versus not good at? Because it's one of those, if you look at individual questions, you can make up why you think ChatGPT got it right or wrong. But like, you don't even know if it's the number of characters, the number of verbs. Like, it's a language model, right? It doesn't necessarily read; it just interprets. So,
I mean, it's funny you should say that. So, one of my colleagues, Gordon Olbacher, he did this. This was early on, so I'm pretty sure the models have improved since then. But he did this test where he said, add fractions like 1/2 and 1/3.
Hot potato.
I actually don't even know the objective.
So this game, anyone not familiar, this one, if you have that little bar counting down over your head, it means you have the potato, basically, and you want to, it's a classic game called Hot Potato.
Yeah, and you want to stay away from those people, or you want to...
You want to stay away from the bar, and if you get the bar on you, you want to bump into one of the other players.
Oh, okay.
But sorry, ChatGPT discussion.
Right, so you know, like if you did things like add 1/2 and 1/3 and show me the intermediate steps, it would do it perfectly fine. You know, it would say, you know, take the least common multiple 6, and then if you did something like, okay, so now show me what 1 over 211 and 1 over plus 1 over 513. So like two numbers that normally don't appear very frequently in, you know, sort of in the corpus that it's trained on. It surprisingly gives you an answer that is close by, and the steps kind of make sense. So it's, you know, like the least common multiple is kind of the least common multiple, but it gets the answer wrong. Like it doesn't get the answer right. So the fact that it's trained on words and not on you know, like math sort of makes sense if you do that. Yeah, it's improved a fair bit. I mean, so this semester, you know, like the class I was teaching, I thought I should just embrace it, you know, like, and I should make, so I let people use ChatGPT on homeworks, on tests, everything.
Oh, really? You just made open ChatGPT?
Yeah. Because, you know, like the students are expected to program during the test and homeworks. Like, you know, when I program, I you know, like I will screw up syntax all the time. So, you know, like it's, you almost need to have like a browser window open. So it would be unfair to test a skill when the way you will apply that skill in the real world is with sort of, you know, syntactic help. So, you know, it's hard for me to tell them not to have an open browser while they're doing their exams. And it's impossible for me to proctor. I mean, maybe I should learn from you. Maybe, you know, I can figure out the way ChatGPT gets questions wrong. But I thought, you know, it actually maybe a better idea to just, they're going to live in a world where everybody is going to have access to technologies like this. So might as well get good at it, right?
Yeah, I mean, especially in the programming realm, right? You can use it to do model code and things like that. It's not perfect, but it gets you.
It's actually pretty good.
Yeah,
it's actually pretty good. I mean, it's not perfect, but it's pretty good. And so it's, you know, I don't know, the skills that are required, like they morph. So like different sets of skills are required. I think judgment is what's. You know, how do you know whether to trust an answer? How do you know how to test an answer?
Well, that's what I like about it is that, I mean, if you incorporate that, you have to know enough to know whether it's right or wrong.
That's right.
Because every answer looks right, and that's
that's
generate an answer that looks right.
Yeah.
All right. So your job on this one is to grab those lights, and then if you have this bar, you try to run it back to the starting point.
Okay.
And you try to get in the way of the other people so they don't.
Okay.
Get back.
Okay.
So now, you're gonna grab that guy. Contra, that's awesome that you played Sneak King. Have you played Big Bumpin? Because that's really the pinnacle of multiplayer gaming is Big Bumpin. I will defend that to the death. So which one are you? You're king?
Yeah. Where am I supposed to go?
This pedestal.
Oh, that's where I was supposed to go. Okay. Good to know.
Lori, welcome to the stream. From Tallahassee, joining us for the stream. Lori has redeemed Take a Drink, so Sachin, cheers. Thank you for joining me on a Wednesday night. Hopefully you guys are celebrating the end of hopefully you're done with finals. If not, hopefully you're enjoying finals week. You're getting the last minute studying in before, I guess the last exams are tomorrow.
Mine was, so I had an awful time. My exam was at 7:30 in the morning on Monday. Luckily everybody was there.
That's good. Yeah, the Gen Chem exams are on Wednesday. They're all block exams. Contra has not played Big Bumpin. It looks like someone looked at Rocket League and went, you know what's wrong with that game? The third dimension. So Rocket League is a version of this, basically. But Contra, I'll counter your point in that this game is 20 years old. And so, as one of my students put it, this game walked so Rocket League could run. And so this is the precursor to Rocket League. Oh, Lori's asking the drink of choice tonight. All right. Killian's Irish Red. And Sachin, this was your choice. You mentioned this being a grad school drink.
Yeah, so I have no particular reason to pick this drink except when I was in grad school. This was the first like colorful beer that I saw after I came, once I started drinking. And I had a lot of it during grad school. And so it just evokes certain happy memories. I think it's
That's awesome.
You know how smells and tastes sometimes have a sense of place.
Yeah.
So this one sort of.
Does this take you back? I mean, is it?
Yeah,
do you like it, or is it just?
I'm not sure whether I love it, but it's a comfy feeling. It's a cozy feeling.
No, we'll take that. I'm glad you suggested. I've never had this before, actually, so I was excited to try. I didn't start drinking till I was in grad school, actually. So
okay.
Yeah, I skipped over the cheaper beer as we drink as undergrads.
Champagne. Okay.
But yeah, drinking some Killian's Irish Red.
Yeah.
It's not actually red for anyone that's curious. All right, Sachin. So we probably asked you this question almost 3 years ago, but we're going to ask it again just because it's where we like to start with things. Is what winding path took you to where you are today, and what were the major milestones along the way that made you said, I want to go into theory, I want to go into soft matter and modeling soft matter? Like, you narrowed down your focus to a particular area. What steps helped you narrow that process?
Yeah. So I think my answer to this question is more of a story fitting the facts. It's like a regression rather than like a set of steps that
right there
that I took proactively. I always liked math and I always liked science, so I knew I wanted to do something there. So I studied chemical engineering, and I actually liked chemical engineering. I was one of those students who actually never missed class. So I was actually a good, a good student from what a professor would call a good student. By the end of undergrad, I was fairly sure that I wanted to be an academic, and then I came to grad school because that's what you do if you want to go to grad school. And up until then, I feel like my interests weren't like sharply defined, and so I didn't know exactly what I wanted to do. Are those things that I stay away from, or?
Yeah, so yours is survival mode. Any of the saws damage you.
Okay.
I can't believe you survived the speed boost.
Okay, not bad.
Oh, yeah. You survived. You just got damaged enough. So yeah, this is survival mode.
Okay. Yeah, so when I went to grad school, the way I picked my advisor was, I thought I want to work with somebody I like, so somebody who's a good person and somebody who's really smart, because I believed in diffusion, so I thought, if I just hang around this person, maybe I'll get smart too. And so the topic was less relevant when I started, and I sort of feel that there are. I don't know if this is universally true, so maybe you should tell me what you think about this. But I feel like for a lot of things, you do a little bit, you get good at it, you like it more, you do a little bit more of it. So the interaction between how good you are and how much you like it, sort of is there's a feedback sort of loop there. And so that's how I ended up in soft matter and my current soft matter and computations and theory. And I never disliked it. The more I did, the more I liked it. And so it was but I don't know whether so when I started grad school, I was fairly certain I wanted to sort of be an academic, but once I towards the end of my grad school, I tried to size up the competition, and I thought, there are people who are way smarter than me, and people who, that's usually not a problem. There'll always be lots of people smarter than you. Yeah. But you can outwork some people and get an edge that way. And I thought, that would be my way of, and then I figured out there's a fair, academia, there's lots of really smart people, and there's lots of people who work really hard. So, it's not just, they'll outwork you and they're smarter than you. And so I had second thoughts towards, I don't know, like my fourth year of grad school.
That's fair.
But then by my fifth year, I shifted again, sort of talking to my advisor sort of helped. And I realized what you don't need to know, you don't need to be the best at everything. You just have to find a niche and sort of learn to dominate that niche. Even if you're not the only fish in that pond, if you're one of the few big fish in a small pond, that's how you make a niche. And so, I mean, that's how that's how I got to where I am. Yeah.
And so did you do a postdoc?
I did. So my postdoc was kind of interesting. So my entire PhD was theory and simulations. And so I thought what I'd do for my postdoc.
Well, this one you want contact time with the puck.
Okay.
So when you touch it, it'll change color orange. That's like you owning the puck.
Okay.
Yep, there. And you get extra time as you own that puck. Sorry to interrupt.
Yeah, so for my postdoc, I thought I should do something radically different. And radically different here meant sort of do something other than polymers and do something other than theory/simulations. So I began doing wet lab experiments.
Oh, wow.
On growing cells on scaffolds. So now I realize I had no business doing that because
but you handled cells. That's cool.
Yeah, I did, but handled and handled well are different things, right?
Yeah.
So I mean, it took me about 6 months to realize I really had no edge, especially. I don't know. I have lots of respect for people who can experimentalists, right? There are 100 things that can go wrong, and you have to have a nose for sort of figuring out. If something went wrong, you want to have a nose for figuring out what went wrong. Right?
Yeah.
And there were lots of people in the group I was in who were really good at that. Your experiment goes wrong, and exactly. The temperature wasn't well controlled, or this. I had nothing of that, and that was, I think, partly because when you do simulations for experiments, you can always recreate the problem. If something went wrong the first time, you can recreate exactly the same problem, and then you whereas here, and with biological cells, I think you could do this really. The same experiment twice, and then you would get different results. And you thought you controlled the key variables, but I don't know. I think Feynman said something like psychology is harder than chemistry because electrons don't have feelings, or something like that. It's I feel like cells are somewhere in between. They kind of have feelings,
well, it's like the error bars are larger the larger the beam gets, right? Yeah.
And so then I realized, I had no business there, and so I backtracked, kind of went back to what I did mostly for my.
I mean, but one thing I'll advocate for is that as a theoretician, that experience for you is priceless, just in terms of appreciating what it takes to do those experiments.
That's right. That's right.
And this is something we deal with, spectroscopy and synthesis, right? The people that make things versus the people that measure things. It's hard to appreciate how hard it can be to measure something. Even if you need one number, sometimes it takes you months to get one number. Likewise, just making something that looks simple can be a super complex problem.
That's right.
I just need 200 milligrams. Well, that's a lot.
That's right.
Knowing that was really, really useful. So I did something similar, not necessarily on the theory front, but as a grad student, I was a synthetic chemist. And then as a postdoc, I did measurement. And now my group does both of those things. Right.
Yeah, I guess that is right. So you get to see...
it's at least appreciate, I guess, is what I would... Wow, look at that.
Yeah.
Misadventures, welcome back to the stream. Soft goods are hot in aerospace right now. Aerospace, NASA, you have any interest in working on
NASA?
Yeah. Misadventures in Astro says soft goods, soft materials.
Soft matter, yeah. Soft matter is everywhere.
That's a good point.
I had one of my so so this is one of my factoids, but I'm going to use
it.
So the Challenger. My sense is some people have already seen this, but when the Challenger space, the space vehicle, when it crashed, and there was this congressional inquiry into what went wrong.
Yeah.
One of the things that that seems to have been implicated are these O-rings,
Yep.
these O-rings.
Yeah, on the temperature. Yeah.
Right, and their failure was actually a viscoelastic phenomena that went wrong, right? So these were supposed to be elastic materials, and elastic materials. So think something like rubber is, when you stretch them or deform them, they snap back into place. And these rings were supposed to do something like that, right? They were supposed to behave elastically. But the day of that launch, the temperatures were, it was a cold day, so it was like 32 Fahrenheit. And these viscoelastic properties of soft matter depend sensitively on temperature. And so what happened was, and this was demonstrated. So Feynman demonstrated this sort of very graphically in front of the Congress. So he took one of those O-rings, he deformed it. So like it's supposed to be like a ring. He deformed it and stuck it into ice water. And then when he pulled it out, it took its own sweet, like it didn't snap back like as it was expected to. It took its own sweet time, a few seconds, and that was enough, right? So in the sort of the rocket boosters, you need something to sort of snap back right away.
Yeah.
And so understanding viscoelastic properties is important.
So related to that story, I recently saw a YouTube video that it was like a 20-minute video talking about that event, and the engineer who knew it was going to happen and tried to warn NASA. He spent the rest of his life feeling guilty about it. But I guess it came down to a graph and how they graphed the temperature versus elastic response. And it's like if there was complete failure, it didn't show up on the graph. And so there was like a threshold they drew that wasn't real. It was weird. It was like a graphing problem as well.
Interesting.
Yeah, I'll have to find that video and send it to you because it was really intriguing.
It's actually a phenomenon that like most rheologists understand. Like so again, just as background, right? So something like silly putty is soft matter because it behaves both like a solid. I mean, you can bounce it, but it also behaves like a liquid. So if you leave it in a tub, it sort of it'll take the shape of the container after a sufficient amount of time. So it behaves. So there's something called a relaxation time, which I think for silly putty is of the order of seconds or tens of seconds. So over that time, or several multiples of that time, its liquid-like properties start. It behaves more like a liquid if you wait long enough. But if you sort of bounce it, the time scale of impact is like 0.1 second, and it behaves like a solid because the time scale of impact is much shorter than the relaxation time. But if you heat it, the relaxation time shifts. So it sort of starts becoming more viscous, more liquid, less elastic. And this is sort of classic, So in a certain sense, I don't know of this graph that you talk about, but I wouldn't be surprised if I trust you that the graph didn't show it, but the extrapolation may have been would have been reasonable for the person who sort of who'd taken a class in rheology.
It was one of those things where like the upper level decision makers used that data to make their decision, whereas the engineer knew it was not complete or something like that. It was Non-dairy, welcome back. All right, Contra has a question. I was wondering how you. Oh yeah, I looked up Contra. You're a streamer as well. You guys should check out his stream. A pianist actually, which is fun. Music theory. That's an engineering exercise right there. That's some programming of musical notes, which I love to hear. So yeah, you guys can check out the stream. But yeah, sorry, the question, going back to it. I was wondering how you decide what you really want to take a deep dives in once you've found yourself in a field. I'm really interested in spectrometry as well. So how did you decide, or how in general do you think people decide?
I have a somewhat simplistic sort of, litmus test. So I think topics worth investigating should either be interesting or important. Ideally both. So if it's one of the two, that's, I think, is sufficient. It need not be important. If it's just interesting, I think that's fine. Because sometimes the important applications are downstream of the interesting. There are classic examples in science, right? So something like liquid crystals. The theory of liquid crystals was worked out in the 1920s, but they weren't used for, I don't know how many, maybe 50 years after that. So there is a reason to pick something that is interesting, even if it doesn't seem particularly important at that time. And then the other extreme is also true. You may want to work on something that is important, even if it is not interesting, because if you make even a little bit of progress, that might impact.
So Sachin gave you the academic answer.
Yeah.
But the reality answer is whatever pays the bill is what we pursue. Yeah. That's only partially true, right? So like we write proposals framed to a specific problem, but maybe we're asking a bigger question or a different question than that. But we do need money to support our research.
Yeah.
So yeah, but it is... it's one of these things when you find an area that you become an expert in, you find where the holes in it or where the new questions are, and you just start to just dive towards those. So,
right. Yeah,
you're doing better, Baba? Is that one of your kids?
Yeah,
there it is. Medhash? Meta Shanbhag. There it is. That's one of yours. Well, welcome to the stream. You should have done an anonymous tag because you could have told me. You could have chatted. You suck at this. You're the worst. Oh, that's pretty fun. Non-dairy neutrino. Got y'all while I'm working on a presentation for computational physics for my high-performance computing class tomorrow. That's fun. Well, you have a professor of scientific computing right here. Any questions you have, any assistance you need, he is happy to answer with you, helping you with your homework.
If that's allowed. Yeah.
Yeah. Did they ever write in the syllabus, you cannot use Twitch as a cheating aid? I say no. Non-dairy neutrino. It reminds me of my undergrad advisor told me, you won't get a grant to do something because it's cool. That's true. You got to sell it as being, well, the hard part is these granting agencies, they're scientists and they appreciate fundamental science, but they also have bosses that they answer to, who answers to Congress, who answers to the taxpayer. And so you have to give some sort of justification for doing what you're doing. So yeah, doesn't mean we can't do cool things. We just have to do it, under the guise of fundable things.
Yeah. Yeah, right.
How's it going? How are you liking Big Bumpin?
Yeah, I'm pretending to know what I know what I'm doing, but I just go.
I imagine this just looks cool for the audience.
Yeah.
So. But yeah, that finding what to do. And the other thing that I've had issues with is wanting to do too many things, right? You wear yourself too thin, you try to pursue too many things, and it's like, because that's hard too. And it's one of those like first world problems that I've like 2 NSF grants, right? And I might have an ARO grant coming up, and it's like I need to fulfill those goals, and you have to deliver and pursue new things that does the next grant cycle. So
that's right.
Yeah, it's a balancing act for sure.
Yeah, but it is, like you said, it is it's a problem of privilege in many ways, because most people don't get to pick the problems they work on.
Well, that's one of the reasons we go into academia, right? We're in love with our own ideas. Yeah. We don't want to answer to a boss other than funding.
I don't know. So when I was applying for academic jobs as I think as a postdoc, I remember, we had these preparing future faculty type seminars, and there was an assistant professor who I remember said, don't go into academia because he said it's the most miserable way of being poor.
I don't know. We do okay.
I think we do okay, but
we're Tallahassee rich, right?
Yeah.
We're not bad. I don't know if I'd want to live on this salary in downtown Los Angeles.
That's right. Well, that's not me. Okay.
But yeah, so speaking of which, I mean, we pursue our own ideas and we want money to pursue those ideas. One of our regular questions we ask is, unlimited budget, no moral qualms, what would you pursue? You didn't have to answer to funding agencies. You just had to go after a problem you thought was interesting or important. What would you go after?
Yeah, Ken, I'm sort of curious what your answer is. I feel bad because I don't have, like, I don't, it's a great question, especially the moral qualms part. Yeah, so let me try. Okay, let me try. So this is not really, squarely in my wheelhouse, but this is a question whose answer I'd like to know, and it's not really. It's more maybe a psychology type question. So just recently, right? So me and my kids and my wife, we were talking about, like this AI stuff, right? So with AI now, you can have immortality in a certain sense. So I could sort of record everything you've ever said, the biggest corpus of, and take all your pictures, and like even after you pass away, I could have a Zoom chat with you, Ken. And it would, because it was trained on you. It would know, like it would respond, and you could make. This is not even tomorrow's technology. This is today's technology. So there's no I think the technological barrier is I don't think is the limiting feature here. But so I asked this to my kids, and I said, would you what do you think about this? Whether you think it's okay if like we keep dead people, episode. like Black Mirror, right? But it's kind of the opposite, right? So I don't want to. I think if it becomes a person, that sort of starts getting creepy even for me. But like if it's just a video, right? If it's just it's like you're watching a video, but now you're interacting with the video. Would that be okay? Like, is that how do you feel about that, right?
What's funny is I was talking about this, talking to a guest about this, because through Ask a Scientist Gaming, there's over 200 hours of me on stream asking questions, interviewing, blah, blah, blah. Someone could pretty easily recreate me and make me say whatever. Right. Like, it's out there. The information is there already. Yeah,
and you have so much video. I think they could make, they could make you say, I mean, they could make you realistically say, wouldn't need too much AI.
Yeah.
But what do you, like, so the experiment I would like to run is maybe just do, and this need not just be after death, but even just having like a friend who's a completely virtual friend, whether that on balance is a positive thing for people, or if it's a negative thing, or if it's if it sort of depends. It depends on context, I don't know. I feel like questions like that it's really large.
That's what makes them fun, though, right?
Yeah.
Well, it's one of those I encourage my students to never lose sight of the big picture. Like, they'll get very caught up in, I have to make this molecule and I have to measure this property, but like, take a step back. What is the real goal of what you're trying to do? And maybe there's a different property or molecule that gets that job done. Similarly, like, what problem are you trying to solve? And does this get you towards the goal? No, try something else. So yeah, I really appreciate the big picture aspect of that discussion.
So what was your answer?
So my answer is it's actually developed over the years of doing Ask a Scientist Gaming. I've had everybody on here, right? I've had like geologists and geographers and chemists and social scientists, physicists, psychologists. I've even had a music theory person on, which was kind of fun. Historians, law professors. And what I come to the realization is we know a lot of things, right? But it's not necessarily common knowledge, right? Cutting edge in law, we don't know, and we won't know for 15 years because it takes time to propagate through the normal population. And so what I'd really like to do is take a compilation of all that knowledge and build a like idealized city from scratch. Like, we're talking like, fluid dynamics. How do you process water? What do you make the pipes out of? What do you make the buildings out of? How do you insulate them? Perfect materials, perfect modeling, perfect behavior. I mean, obviously it won't be perfect, but like, can we make an optimized city from what we know? And you could make an optimized like schooling system based on cutting edge pedagogy. You could have, the economic system based on theory that's present. Like, what would a cutting edge built from scratch city look like?
But do you think there's one answer to that?
I don't think there's one answer, but I think there are general consensus, right? Like in terms of like, what would be the ideal material to make, pipes out of? Like there are right and wrong answers to that. And so could you get a general consensus? And your budget's unlimited, right? So you can make it perfectly durable. You can make it forever. You can make this thermodynamically perfect, like solar driven, I mean, what kind of city could you develop? What kind of economic system? What kind of political system? What kind of law system would be the byproduct of that?
Yeah.
So that's my big answer.
It's an interesting question, but I mean, I haven't thought deeply about this at all. But I don't know. Like, I worry if there is one answer, and it's in a certain sense, you're asking a question like, what's the good life, but at the societal level.
Yeah, exactly.
I feel like answering that at an individual, personal level is hard enough.
No, that's it. But I mean, there's certain things like, and I learned this from it was Brad Johnson. He's in the geography department. He does facially mapping of cities and stuff like that. And one of the things I learned that was interesting is there are European cities where the roads are oriented such that it coincides with the airflow through the system. So it like uses the what is it called, Venturi effect or whatever it is when you circulate air through columns, and that's how you keep the smell down and you keep it cool. And like little things like that, you accumulate a million of those little things, and you have designed a crazy spectacular city. So
that's interesting.
I would love to compile all my experts and draw a legendary city.
I think I think a more modest thing. I mean, more modest, like a personal type goal, can be just learning these ideas. Maybe you already know because you've been doing these podcasts. But like, I feel like there's like a few big ideas in every discipline. If you just compile them.
I think that's all it would take. I mean, that's what I really appreciate about doing this stream is every stream I learn something like. And some of it's like intuitive, like, duh, that's true, but now we have the evidence to support that it's true. And others are like, that's super counterintuitive, but this is what the data says. And it's said it for 100 years. We just don't accept it as reality.
That's right.
So,
yeah.
That's Contra. Thank you. Yeah, I'd be interested in the imaginary city. Lori, wasn't there a movie recently where someone fell in love with a virtual person? I mean, that's Her, I think, was one of those. Her.
One of the have you watched Ex Machina?
Yeah, exactly.
Like, that was a good movie.
Yeah, that was spectacular.
Yeah.
Ex Machina was a really good one. Her was one. He fell in love with the AI. I think.
And was there I don't know if. Oh yeah, that was her.
Yeah, Ex Machina.
So this whole debate about AI, whether it's like electricity and it sort of permanently improves humankind, or if you've already given birth to the sort of the technology that will eventually like decimate us. Like, where do you fall on that? Where do you fall on that spectrum?
Sorry, say that again. I was copying movie quotes.
I feel like there are people who are excited about AI because they think it's like human productivity is going to improve tremendously because of that. Like, it's like the new electricity. And there are people who think, like smart people who think that this is all bad because this is how humanity ends. So where do you sort of fall on that spectrum? Or
man, that's one of those, like, I can envision how AI could make all our lives better, but if history is any indicator, it's been 200 years of technology will make our lives easier. We'll be able to work less. We'll be able to relax more. And that the opposite has been true. We've worked longer hours. We've spent more time working, and it hasn't made lives better.
That's because we live in America, right?
Exactly. Well, and that's a byproduct of capitalism, right? The capitalism at its heart, sorry if anyone's upset about this or a capitalist at heart, is that, like, your goal is to make as much money as you can while screwing over other people to an acceptable threshold. Right, you can't screw them over too much, but you're not out to help them either. So it's depressing but true, right? And that's what AI is going to do, right? It's going to be exploited to make somebody money, but not necessarily make most people's lives better, unfortunately. At least that's my prediction. So that's cynicism, not about AI, but about the system we exist in.
Yeah.
What about you? Where are you on that spectrum?
So I've spent a lot of time listening on this issue. I haven't like synthesized my thoughts into something whole. I am not sort of existentially worried just yet. I think it'll do a lot of good things before it does bad things. And I don't know whether we actually have any control anyway.
That's a good point.
It's like the cat's out of the bag.
Yeah. Misadventure. When the automatic machine gun was created, many people thought it would end wars because it was so terrible.
Yeah.
Oh no, we found better ways.
Yep.
Man, that's an existential dive though, isn't it? It's something I lose sleep about at night. Not like every night, but it's one of those, like, if that thought gets in your brain and you try to wrestle with that just on a personal level, it's challenging. I think one thing that's inevitably going to have to happen is some sort of universal basic income.
Yeah.
I think that is going to have to exist. If you replace, 30% of the workforce that drives vehicles with self-driving cars, you don't invent new jobs to replace that. Like, people need to survive, so. Well, you're tearing it up this round.
Oh.
It's going well. Automatic machine gun. Contra. I come from having read most of Hofstadter's material that he'd written, and that is the limit of my education on this subject, but it was the most fun education I've had. Hofstadter's pretty spectacular. Self-referential loops and...
Yeah.
What was the... He did Gödel, Escher, Bach, and I Am a Strange Loop. Yeah, those are fun reads. But again, existential nightmares. All right, while you're playing the game, Lori has requested a factoid.
Oh, okay.
Factoid knowledge bomb you want to drop.
So
you good on beer? You want another one?
I think sure, I'll have another. So I wrote one down. Okay, so maybe so many of you are probably familiar with the parable of this guy who goes to a king, and the king, he does something that the king pleases, that pleases the king, and then the king says, you can have whatever you want from my kingdom, and then the person says, like, I want 1 grain of rice, like the first square of a chessboard, and double that on the second, and so on. And then by the time, so you do 1, 2, 4, 8 grains of rice, and by the time you get to the 64th square, because a chessboard is 8 by 8, so there's 64 squares. The total number of you can sort of count how many grains of rice that would be, and it's it's not too hard to show that it's 2 raised to 64. Which, if you if you assume like whatever 10 grams per grain of rice, or whatever the appropriate number is, turns out to be more than the sort of global annual production of rice. Right? So it's just the compounding and like the doubling really gets you, because the 63rd square is half, but the 64th sort of doubles. Like the doubling is problematic. And so the reason I thought that was an interesting parable is because it ties to scientific computing or computational science in a funny way. So maybe all of you know that that there are real numbers, right? So real numbers are numbers like 1 and 3.5 and 1/3 and square root 2. So they can be rational, they can be fractions, etc., etc. And you can sort of graphically represent that by a real number line, which goes from -infinity to +infinity, and is infinitely dense, right? So if you give me any 2 numbers, I can give you an infinite number of numbers between those 2 numbers. So you can give me 2 and 2.1, but there's an infinite number of numbers between 2 and 2.1. Maybe you say 2 and 2.01, still an infinite. So it's infinitely dense, right?
Yep.
But the way real numbers are represented on the computer is with something called floating point numbers. So the floating point numbers are a caricature of real numbers. So they are meant to represent real numbers, but they are not infinite. So there's a maximum number that you can represent, and there's a tiniest number out next to 0 that you can represent. And then it's like, you should think of it as like as a fine-toothed comb. It's it says each tooth of the comb standing for one number that is represented by this floating point number. And it turns out that most modern computers, they represent, they use something called double precision, which uses 64 bits to store a floating point number. And so there are as many floating point numbers as there are grains of sand in the previous example. So it's a lot. It's something like 10 to the power of 19. So there's a huge number, gazillion, but there's still a finite number, and that actually create. I mean, the fact that we represent every number using these 64 bits helps optimize lots of things. Like adding numbers is easy, subtracting numbers, because they are all the same format, so a computer knows what to do. But because there are holes on the number line, that creates, what are called round-off errors. And that's like that's a big source of what a computational scientist like me worries about. So I thought that was a sort of a interesting connection between the fable and the way numbers are represented on a computer.
No, that's fun.
Yeah,
it's infinite numbers, but you can 64 bits.
Yeah. I mean, the whole idea is like if I give you like 4 decimal places and asked you to represent a number like 1/3, you would do 0.3333, and then you're not done yet. You've left something out, and what you've left out is the round-off error.
Yeah.
Same thing with 2/3 is you can write it as 0.6666, but you've left something out, or maybe you do 0.6667 because you round up, but you still left something out. And when you deal with huge systems, these tiny sort of round-off errors can come to bite you. In fact, that's the only thing you worry about when you do something called linear algebra.
That's interesting.
Yeah.
That's the plot of, what was it, Superman 3, Office Space? Have you seen Office
right?
Space?
I've seen Office Space.
The rounding error where they took the rounding of the number
right, the 80
to a cent.
Was that Office Space?
They took a fraction of the cent and they put it in a separate bank account.
Yeah.
Those little rounding errors matter a lot.
That's right. Yeah, they do matter.
All right. Speaking of big numbers and intuition, you can go ahead and start another game. I'm going to put a prediction up for you guys right now, and it's related to big numbers and what your intuition is on this. So those of you not familiar, predictions on Twitch, typically people use them to, predict whether Sachin will win the next game or not. For us, we use them for science questions. So every guest I have on stream, they put together some science questions that I'm going to ask of you, the audience, and you're going to be able to gamble your standard internet units. So if you're not following us, click the follow button, get your 300 standard internet units. And what's going to happen is I'm going to pop up a question right now. You can click the predict button. The question is, what are there more of? Shuffles of a 52 card deck or the number of atoms in the universe? Both of these are going to be giant numbers. This relates back to the grains of rice and how it doubles and things like that. Both of these are gigantic numbers. The question is, which one of these is bigger, the shuffles of 52 cards or the total number of atoms in the universe? So yeah, click that predict button. You can gamble as many of our standard internet units as you like. They are useless outside of the stream, but they can buy you a factoid, or you can force us to drink, or you can unlock emotes. But again, if you're not following, click the follow button. It helps with our numbers, but also gets you some standard internet units that you can gamble, and you'll get notifications about our streams, which we have every other Wednesday night we'll stream. So what are there more of? And note, you're on Ask a Scientist Gaming Honor Code. You can't look this up on ChatGPT or Google or whatever it might be. I'd be curious how ChatGPT is.
Yeah, you should. Yeah, we should check that. Can you open a browser?
Yeah, I can do it.
Yeah.
See if I'm logged in on this computer.
I have a feeling it's gonna get this right. Maybe we should wager on whether it will.
That's a good question. Will ChatGPT get this question right? Yes or no? Oh, there we are. I'll turn it into multiple choice. I'll give it an A and a B. All right, let's do this, ChatGPT. See how it does on this question. All right, ladies and gentlemen, you have about 5 seconds. Put your guess in there now. Is there more shuffles than 52 cards or number of atoms in the universe? What is your guess? All right, Sachin, what's the answer?
So in a certain sense, this was. So there are more atoms in the universe. So the universe, depending upon, and these are of course estimates, has between 10 to the power of 78 to about 10 to the power of 82. So that's 1 followed by, let's say, 80 zeros, those many number of atoms. The number of shuffles in a 52 deck card I mean, for those of you who took math, you probably know that's 52 factorial. And that turns out to be a really large number, but that's only 10 to the power of 67. So 1 followed by 67 zeros, which is about a trillion smaller than the number of atoms in the universe. And the reason that I thought this was interesting is because, I mean, many of you probably know that a Google is 10 to the power of 100, right? Mm-hmm. It's probably I maybe there's Googleplex too, but Google is probably maybe the biggest number that has a name, or something like that. And so I guess a question I thought of was, is there actually a Google of anything in the world? And it turns out, like, there is not a Google of atoms in the universe, and you can try electrons or things like that, but that just adds it's just going to increase that, because like, even if it's
you're not having 100 electrons.
Even if every atom had 1,000 electrons, that would just give you 3 more orders of magnitude. It's not going to get you to
Google of anything. Google of photons.
Maybe, but so the easiest way to get to large numbers is to talk about combinations. So while one deck of cards is, like the number of independent shuffles of a single deck of cards is 10 to the power of 67. If you think about 2 decks, so you do 52 plus 52, which is 104 factorial. That's well over a Google. That's like, that's twice the number of atoms. Not twice. It's like whatever. It's a square of the number of atoms in the universe. It's like 10 to the power of 160, if I remember right. So that's the only way you get to sort of, like combinations is the way you get really large.
Oh, that's interesting. Non-dairy neutrinos. I think the heat death of the universe is predicted to happen around a Google years.
A Google years?
Yeah.
Oh, that's interesting.
Google of years, yeah. I mean, that's one of those things, those like time scales.
Yeah, maybe, because you get to define the smallest unit of time, because you can always say I can go picosecond or femtosecond or attosecond. You can say my unit of time is 10 to the power of minus 100 seconds, and then 1 second has a Google of those. Right?
Yeah. No, that's true.
Yeah.
Scales of time, like resistance and things like that. Yeah.
But what's like what's the smallest? I don't know. Is there something like the smallest time scale?
Smallest measurable time scale is an attosecond right now. Something like 30 attoseconds.
Right. So like, forget measurable, but like, I mean, if I don't know how to frame this question, but like, what's the fastest thing over which any change occurs?
And that's I think that's kind of where that comes in. So like, if you're going to do any change of any kind, you have to move electrons, right?
Right.
To watch an electron excite from a ground state to an excited state is on an attosecond time scale.
And atto, remind me, is what, 10 to the power minus 18.
Yep.
Okay, wow, that's quite a bit.
Yeah. And then on the other end of the spectrum, we have the heat death of the universe.
Yeah,
10 to the 100.
10 to the power of 100. That's a lot. Yeah, that's huge dynamic range. To me, that's how,
Yeah. No, that's fun. All right, congratulations, anyone that said number of atoms in the universe. So when I was searching for these numbers, I found a couple different versions of this. Okay. If you do the same question shuffle in a 52-card deck versus number of atoms on Earth, then the deck of cards is larger. And so that's
on Earth, yes. Sure. And
so that was one of the more common versions of this I saw.
Okay, yeah.
But if you guys were curious how ChatGPT did on this one, it got it correct.
That's right. Yeah.
And so I gave it the multiple choice answer, and here's its rationale if you guys want to read it in chat. But there it is, comparing the numbers, blah, 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 10 to the 80th versus 10 to the 67.
Wow, that was like my answer.
Yeah, no, it gave the numbers. And it probably got the same Google search you did.
Yeah, probably.
There it is. 30 atto. All right. In statistical mechanics, there's a good old law of large numbers. It says a large number plus a small number is the same large number. A very large number multiplied by a large number is the same large number. That's true. I had a friend that was, he did like mathematics classes, and like, it's like, oh, what's infinity times infinity? Well, it depends what infinity you're talking about. There's different flavors of infinity.
Number of points on a line or number of points in a square. Yeah.
Oh man, we got existential there for a while.
Yeah.
How are you liking Big Bumpin? What do you?
Yeah, like I promised, I haven't gotten any better over the half an hour of playing it.
No worries. And we missed one. I think your other kid, Jill Y. Bean.
Oh,
I met his
that
dad.
could be her. I don't know. Like
It said dad.
she's using,
Anonymous. Dropping lines in chat.
It's like her to do that.
Yeah. When is their bedtime? Are we are we ruining it?
They sleep at 9:30, but I don't know.
That's fine. They got a half hour. They can hang out and watch some Big Bumpin. But yeah, if you guys have any questions for Sachin Shanbhag, he's happy to answer anything about soft materials matters, polymers, whether they're natural or synthetic. He's very interested in polymer properties, particularly mechanical properties like rheology. That it's a really cool measurement if you want to explain that at some point. But yeah, modeling those materials is non-trivial, but it has a dramatic impact on the day-to-day life of things you handle, things you do. I mean, even what your car is made of and how they clean it, how they process it, how they heat treat it is all dictated by those things. Non-dairy, I apologize if I missed a comment. I try to keep up with chat, but I also like chatting myself, so I kind of asked before chat was moving, what kinds of computational tools do you use in work and why? So what software, what computers, clusters, what do you do?
Yeah, so I use I've programmed in lots of different languages, use lots of different software. Right now, I do most of my programming using Python. Python has, I don't know, for scientific computing, it's sort of become the language with which you interact. So even though there may be like C++ or Fortran or Java, like some low level language hiding behind, Python's become the interface.
It sounds like that's been pretty universal across the computation board. It's just a better interface. Is that?
So I am a somewhat of a newish convert to Python. So I didn't use Python until 2014 or 2015 when I was doing a seminar with one of my colleagues on Monte Carlo, and he suggested we should just use a common language just so that we can compare notes and stuff like that.
What did you use before that?
I used a mix. So I've programmed in Fortran and C++ quite a bit when I was in grad school because that's what you did.
Yeah.
And then I continue to do. I still program in C++ every once in a while, but increasingly more and more Python. And then I've used this language called Julia. I think we talked about it a little bit the last time I was here. And so, I haven't sort of completely converted to it, but it's a language that I can imagine and see myself moving to, just because it offers this nice blend between a language like Python, which is just fun to use. It has, so the really cool thing about Python is that it has a rich library. So anything you want to do, you can actually do it relatively fast. You can reproduce something that you've seen in a paper, like hot off the press paper, on the order of days. It's just so fast. Especially if you're working on something like machine learning or I don't know, like molecular dynamics, etc. The code base for like a lot of them, if you understand sort of the theory, just implementing it on a computer. Has been democratized so much, and I feel like Python is super at all that. I used a little bit of MATLAB and something called Octave, which is like a free version of MATLAB. Once upon a time, I've sort of mostly abandoned it. I use it in the class I teach because I'm expected to use it, but then Julia is kind of nice because it's super fast. It has a rich library. It's very modern, and so like you were talking about the city, right? It's learned a lot of good practices from sort of other languages. And unlike other languages, it was designed by people who do computing for science. So, with number crunching in mind. It was not designed by computer scientists to solve computer science type of problems. It was designed by scientists to solve science problems that needed a computer. And so the choices you make are, like different when you have a different orientation. So I like it a lot. It's just that there are a few annoying things about it even now. There are features I love, but there are some things that are just annoying that I haven't got over. But either they will change or I will change or some combination of both. And I can, and what Julia also does, kind of being nice, is you can abstract hardware much better. I mean, you can do that with Python and if you're using a package too. So you can run, like a molecular dynamics simulation on using MPI on a CPU cluster or a GPU or whatever without sort of having to deal with the nitty-gritties of actually implementing it on different architectures. So you do the same stuff. I mean, we're almost there. You essentially tell the computer what to do and you say, I want you to run this calculation on this hardware. And it kind of does that. It's not automatically, but close to, like if you look at where we are now versus 10 years ago, I mean, I wouldn't have thought you would come this far this soon. But in computers, I guess you should get used to sort of exponential change improvement.
So that's the programming language. A lot of the models you use, like Monte Carlo simulations and Bayesian statistics, and you said molecular dynamics simulations. Anything else on top of those, or are those your go-to?
I think that's primarily it. I do lots of methods development. So, so maybe there's a certain class of equations somewhere and you want to sort of try and solve it. They're like just developing efficient methods. So if you have a particular problem, then you can use you can exploit the particularities of that problem to design like super efficient methods to solve those problems. And that's what I try to do, like find specific, like you don't have to solve the most general problem. You solve the specific problem in the most efficient way you can.
Non-dairy neutrino. This is probably a new comment that's been chatted into Twitch for the first time. Julia hype. I'm using it for my master's thesis and honestly think it's the future of scientific computing. Between its performance compared to Python, ease of parallelizability, and support for other high-performance methods like GPU computing and being open source compared to platforms like MATLAB and Mathematica, allows for reproducibility and accessibility.
Absolutely, yeah.
I think Julia is going to be a strong contender going forward for computational science. If you had to put your money on it, Julia versus Python.
I mean, for scientific computing, I can, so Julia's has been around now, I think almost 10 years. And every couple of years, I give it a try. And then, and I think the best way to sort of try is to actually just do an entire project. Like if you're working on a problem, just do it in Julia. So I've done it on a couple of problems now. And I mean, it's great. I mean, there are features that are like total killer. But then, I don't know if this is just being old, but you are sometimes used to certain things behaving certain ways, and it is extremely annoying. So for example, I've never liked the way plots look like in Julia or how to control plots. I know this is like silly, that's like the last thing you should worry about. But like when I'm prototyping, I like plotting things a lot because I'm still building my intuition on the model, and I like to see things. And like Julia's a decent. Like if you came to me 15 years ago and gave me that library, I would have thought this is like this is super. But now I've just gotten used to sort of the plotting features in Python, and I think I don't know. I'm so used to them that just learning something new. I know this is inertia. This is not on Julia. This is on me. But still,
yeah. I get it. You've gotten old. Get off my lawn.
Yeah, the science progresses. We're one funeral at a time, right?
Exactly. No, that's awesome. Not dairy, though. I'm glad you can connect with Sachin on that front. Man. So I was talking to Eugene Prince about this at some point. Like, he's in a unique position where he takes students in that essentially have very little programming experience because he's, he's a programmer that works in the chemistry world.
Right.
I imagine the students you get, I mean, in scientific computing, they're probably more adept at programming, but still, I mean, a lot of them are still starting from a pretty basic standpoint. So what's your routine with a new student? Do you give them a like hello world exercise, or do you have a specific?
So actually, my problem, I think, so if Eugene and I sat, the intersection of our problems, our programming problems, would be almost a null set.
Yeah.
So I get the exact opposite. Like like my first student, my first PhD student, like he was such a good programmer. Like he was a much better programmer than I think will ever be. So like extraordinarily careful. Like my only frustration with him would sometimes be that he would write, when we do science, it's different from writing code for, let's say, Microsoft, right? So or sometimes you write code that is built to last decades, and sometimes when you're actually doing research, you want to prototype fast. You don't care if the code is clean, but you want to try an idea out. Maybe there is time to clean it up later. I mean, that's what we tell ourselves. I mean, but he would write like pristine code. Like his code was like poetry. Like you could stare at it and sort of get, like, it would evoke emotions. Like it was literally that good, right? So it was that good. But like when you build something that good, you have to do it. You have to do it slow, right? So it comes at the cost of speed.
Yeah. And is it worth it for a one-time application?
Yeah, that's the question, right? Yeah. And I'm sure, So I don't like. I have an opinion. I don't have an answer, right? On that question.
That's fair. Contra, if you want to know which one Sachin is, he is the king.
He doesn't know what he's doing.
Top left corner. He's the king. You'll notice him standing still sometimes.
No, I sometimes wonder who I am and why I'm not moving, and then I realize I'm looking at the wrong person.
He's the red one, and somehow they're winning. That's why this game is perfect. Sasha, they're like, oh man, he's so good at this. It's not even you. Oh. Man, I like it. That's why this game, I think, is perfect for guests that don't know what they want to play. Non-Dairy followed up on the discussion. Oh yeah, plotting. I still think Mathematica has the rest of them beat by a mile when it comes to visualization.
Yeah.
Agree or disagree?
I'm not sure. So I stopped using Mathematica for my, for work a while ago. So I will occasionally pop into it, largely because no.
I love it when they make it.
I thought it was gonna go in. Okay. You called me, and then
that was a physics problem right there. That was amazing.
That's right. Yeah, so I think if Mathematica wasn't as expensive as it is, it would be, the best piece of mathematical software. Just to do math type of problems, whether it's symbolic, even the numerical even numerical stuff has improved so much. And we recently had a seminar in our department from one of the folks at Mathematica. And their machine learning. So if you say, make a plot, I mean, you can do all sorts of stuff, all sorts of stuff. Like it integrates a browser, and you can just directly ask it to do stuff, and it'll do stuff for you. I mean, it's amazing. It's just expensive, and I sort of realized this the hard way.
Oh no! 3 seconds left. They scored. Sorry,
it's just it's sometimes. I mean, when you do research, your research lasts decades. So I will use a program I wrote 15 years ago every once in a while, and so you want to use software that is durable, like something. I could buy Mathematica, that's no problem, but in 10 years, Mathematica will be 3 versions further out, and my programs might not work or might do something funny. I mean, this happens with stuff like Word and Microsoft too.
What's the cost per seat of Mathematica?
So it depends. So I don't know what a individual license is, but my department has a license because we teach Mathematica in a certain class.
I see.
And it's not that cheap. I actually don't remember what the.
I mean, it's probably 50, 60 grand for the department or something, right?
So we have just 10 seats, so not more than 10 people can use it at once. And I think it's a little bit cheaper than that, but it's way more than like what use we extract out of it. So I don't think it's, and and they'll say take it or leave it. So I mean, that's the only thing I sort of
Oncom Music, welcome to the stream. First time chat. Thank you for joining us. Their sentence: I never expected Mathematica to be discussed on Twitch, but it's great.
Yeah.
Not only is it discussed, but it's discussed while we're playing Big Bumpin, which is a 2004 Burger King game that very few people know about, but it is excellent. You guys should all try Big Bumpin. Find an emulator, find some way of playing it. It is spectacular. But yeah, welcome to the stream. Thank you for joining us. Our guest today is Dr. Sachin Shanbhag. He's an expert in soft materials, modeling materials. He's talking about different programming languages and what he uses to model those materials. So thank you for following us. Thank you for joining us. You'll get a notification every 2 weeks when we stream with different guests. And it's been a run of theorists. So 2 weeks ago we had Hitesh Shanglani from physics, who does condensed matter physics modeling and things like that. So yeah, theoreticians. And then in 2 weeks from now, I have one of your colleagues on, Brian. I don't know, Quaif. That's his last name, but yeah, he'll be the guest on as well. So we have a theory run on Ask a Scientist Gaming. But yeah, we discuss things like Mathematica while playing Big Bumpin and drinking. So cheers to anyone that has a drink in hand at FSU. It is finals week. So Sachin and I are celebrating, relaxing as we unwind for the semester. Do you have anyone graduating this semester?
No, actually he's defending over summer. I don't know whether he's.
But not walking on Friday.
No, not this Friday. No.
But cheers. Thank you for joining us. Thank you for the follow. Meta Shagbog, thank you for the follow. Thank you for joining us. Your kids follow.
They were surprised that I knew about Twitch. I told them I'm going to be on my friend's Ask a Scientist, and he's live streaming on Twitch. I mean, they looked at and they were surprised. It was. They looked at each other before they looked at me because they weren't sure that they heard me right.
You knew what Twitch was.
I mean, look at me. I suck at video games. I use the.
That's what makes it fun, though.
Yeah,
and that's one of the key reasons I started.
Tell me what I'm supposed to do. Am I supposed to chase the guy with the bar?
You get the things with the light. Go with the light and bring it to the center point. Sorry, I completely didn't coach you.
No, you're fine.
Capture the light, bring it to the center. The more bar you have by the time you get there, the more points you get. So yeah. But yeah, that's the thing about Twitch is it's not the best video gamers that get the most views. It's the most interesting people. And Sachin, I'm going to say you're an interesting person, so your gaming doesn't matter.
That's right.
At least our literal dozens of viewers would agree. But yeah, if you guys have questions for Sachin, he's happy to answer them. Talking about anything soft matter, soft materials. We should probably do another prediction. We're due. Which one do you want to do next?
Which one do you think? So let's do this one.
So Non-Dairy said, it looks like Mathematica pricing for colleges and universities is between 1,630 per year.
That sounds about right.
Is that per seat or that's just?
I think that's per person.
That's per okay.
Yeah.
So if you have 50 Wilhelms or whatever, 50 Steinens wandering.
Yeah.
On Twitch, it does seem to matter how nice one's bathtub is for some reason.
What does that mean?
So there's a contingent of Twitch streaming, like there's science streamers, there's video game streamers. Within the last, I don't know, what has it been, 2 years, they started a hot tub subcategory. So it's like the OnlyFans contingent without the nudity of Twitch. And so yeah, Contra, just wait for us to do Ask a Scientist Gaming Hot Tub Edition. Me and Sachin sitting in a hot tub playing video games.
Yeah.
That's how you get the views. That's how you reach the people with your science. It's through hot tub streaming. Ask a Scientist OnlyFans. It's coming. Sorry, Sachin. Which one are we going to do? Which question?
Let's do number 2 there.
This one?
Yeah.
Oh, that's a fun one. This is a classic chemistry demo, actually. Contra, if you've tried playing piano from a hot tub, has that worked for your stream? I'm sure somebody has. Somebody had to have had. It's the Lindsey Sterling strategy of playing violin is not enough. You got to dance while doing it, kind of thing. Yeah, you need piano and hot tubbing. That's the key. That's how you get the views. All right, ladies and gentlemen, we're going to put another prediction up there now. If you guys aren't following us, click the follow button. You're going to get some standard internet units. You get to gamble them on a science-related question. And so this one's a classic chemistry demonstration. We often do it for kids all the time. If you take borax and glue and put them together, you get this slime, and it's like a non-Newtonian fluid,
yep,
right?
It is, yep.
Which we'll dive into later, because that's a really interesting problem. But the polymer in that mixture, the borax plus glue, the slime it gives you is a polymer. Where does the polymer come from? Does it come from the borax or the glue? What is the source of that long chain of atoms that makes that polymer-like property? My piano didn't appreciate it. I tried an electric. It talked back, and now my hair stands up. I appreciate the effort. I'm glad you tried. Maybe for 1,000 followers, I'll do an astronomy from a hot tub. Ask a Science Gaming crosses 1,000. Actually, we're not that far away. We're only at 747 followers, so we're pretty close. Maybe we'll do a hot tub stream. Actually, fun for you guys though. Are you familiar with Discovery Days in Tallahassee? It's where they have like the science and educational aspect. There's like a week of science activities. So I got an invite to stream live from the Challenger Center planetarium.
Huh.
So I'm going to transplant this setup. They're going to project on the planetarium screen. We're going to do live Q&A from Ask a Scientist Gaming.
Oh, cool.
And so I think I'm going to have David Collins, our astrophysicist, on. It's a planetarium.
Yeah, sure. Yeah.
Makes sense.
That makes sense. Yeah.
All right, you guys have about 30 seconds to answer the question. Borax plus glue equals slime. That slime has a polymer. Where does the polymer come from? Is it from the borax? Is it from the glue? Where does the polymer come from? I've always wondered this exact question. I can't even vote. Wait, why can't you vote? You should be able to predict something. Dark horse bet by Misadventure. Oh, 5 seconds. All right, Sachin, what's the answer? Where does the polymer come from?
So the answer is glue, right?
Oh, wow. The dark horse bet wins. Congratulations on your 5.1 to 1 payout. Misadventures, you took the win. Congratulations. The polymer comes from the glue. So what does the borax do?
So the polymer is a polymer called polyvinyl alcohol, I think. And it's just a regular polymer, and the borax is what is called a cross-linker. It takes these polymer chains and then it sort of connects them to make a network of polymers. And so these polymer networks tend to be sort of much stronger in general. In fact, rubber tires, the story of how rubber came to be used in tires follows, similar chemistry. You can correct me if I'm wrong, Ken. Mm-hmm. But so natural rubber, the rubber that you can extract out of latex, that turns out to be not a particularly durable material. I mean, its properties degrade very quickly with temperature. It cannot handle, like salt water would sort of, make its properties degrade, etc. And so this process called vulcanization, so vulcanized rubber, and you put sulfur and you cook the rubber in it, and the sulfur acts the way borax does in slime. So it sort of binds chains of rubber, and rubber itself is a polymer. It's some type of like a polyisoprene kind of polymer, and that gets cross-linked into a network, and that gives that's why you can drive. So the tire you use now, I don't know if they still use sulfur, but they use something similar. The technology is similar, and that's what enables you to drive your car. Regardless of whether you're driving it in Michigan where it's minus 20, or you're driving it in Arizona at like 120. So it has the range of its operation is fairly wide. Very different from O-rings, right? Which weren't designed to handle freezing, right? So it just goes to show you, like with polymers, you can do a few things here and there, and you can change their viscoelastic properties. And if you don't pay attention, you can have disasters. Mm-hmm. And if you are careful about that way you do it, you can get something, that sort of, that can be used really widely.
I mean, so the glue in this case, just like Elmer's glue, it has a polymer of some kind. Do you know what happens? Well, like how to describe the drying process and what it does? I mean, is it just intertwining?
That's right. That's what. So lots of adhesives are polymer based, right? And then like some of them, like some of these epoxy based adhesives, like they will do they will have some cross linker, which when it dries, sort of becomes a network and binds. I mean, you can bind metal and metal also, right? So sometimes. So one of the applications of polymers is adhesives, right? And they follow something very similar to what you said, right? So they dry out, so something dries out, and then
that makes sense. So contrast, a follow up on that. So the borax just boron, or is it meaning sodium borate? Does the sodium have anything to do with the process? I don't think so. Sodium's a spectator.
Yeah, I think it's boron.
It's a boron that does the linkages, and I think it does 3 bonds, and so it does cross linking rather than just Yep. So sodium is I think something we describe as a spectator ion.
What happens to it? I don't know. It's just sitting.
It's probably in there somewhere. I mean, it's still charged. But yeah, you can think of it as spaghetti, and then the boron like ties the spaghetti noodles together.
That's right.
And it's called cross linking.
Yeah,
which is pretty cool. It's a polymer property. But yeah, so you make that slime, and it's a non-Newtonian fluid. Can you describe what non-Newtonian fluids are?
Yeah, so I mean, I probably used this explanation last time, but
before you go into explanation, go Haku, welcome back to the stream. Just rejoined. Pinball racing? No, we're playing Burger King game Big Bumpin for the Xbox. That was from 2004. Burger King released a game too good for the internet. They decided to sell it on Xbox, so we are playing Big Bumpin. And our guest today is Dr. Sachin Shanbhag, who's an expert in soft materials. Anyway, sorry, non-Newtonian fluids, go.
Yeah, so non-Newtonian fluids are materials that are intermediate between solids and liquids. And so they, they exhibit properties of solids like elasticity, and they exhibit properties of liquids like viscosity. And so, if a classic like slime is an example. So is silly putty that I mentioned before, and so is so are many things that like foam or toothpaste, etc. I mean, if I asked you what state of matter was, let's say glass, you would probably say solid. Or let's say what state of matter is ice, you'd say solid. If I asked you what state of matter is a liquid, is water, you'd say a liquid. But if I asked you what state of matter toothpaste was, you'd have a hard time, because toothpaste, like a solid, can hold its shape indefinitely. But when you squeeze it or you squirt it out of the tube, it flows like a liquid. So it has, so toothpaste is also a viscoelastic material or a non-Newtonian fluid or soft matter. I mean, these words are for the most part interchangeable. And so the Newtonian fluids are did you say non-Newtonian? You said non-Newtonian.
Yeah.
Okay, just making sure. So non-Newtonian fluids are that. Newtonian fluids are fluids like water and honey, which do not have any elastic properties. Yeah.
Yeah, and one of the things, correct me if I'm wrong, but that slime, it has a mechanical resistance, right? If you hit it hard enough, it turns solid.
So it has a modulus, yeah. So it can hold its own shape, and then if it has a modulus, then it will act like a solid at some time scale. Like you could, again, silly putty is a nice example because it has a relaxation time that is of the order of tens of seconds. So you can see it as a solid when you bounce it, and you can see it as a liquid because you leave it in a tub and it sort of, it evens out. It flows like a liquid. Same thing happens with any non-Newtonian fluid, but the time scale at which, if it relaxes really fast, you will have to go faster than that. In a certain sense, I mean, the fact that water is, I don't know, I'm speculating, but I think I'm speculating intelligently. Like water is a Newtonian fluid, but that's also an approximation. My sense is if you
extreme,
like at a femtosecond or something like that, water would be like a solid. So if you can imagine jumping from a really high a plank into like a lake or a pool, like if you jumped really high enough and assuming there was no air resistance so that you didn't hit terminal velocity, you could actually hurt, it would go splat on the surface of water.
Surface tension matters at a certain time scale.
That's there too. Surface tension sort of
Yeah, that's man. So the Department of Defense is very interested in this problem because they want soft materials that are responsive and turn hard under a explosive force or something like that. Right? You coat a car in this, and all of a sudden it's resistance to impact if that impact is of a sufficient time scale and threshold and whatever.
That's right. So,
Newtonian force. So yeah, super important problem.
That's it. So there are like bulletproof vests. I mean, some bulletproof vests. I mean, the most popular material is probably
Kevlar.
still Kevlar.
Yeah.
And Kevlar is a polymer too, right?
Yeah.
So, and what you want a bulletproof vest is not just to resist the direct impact. It's got to be hard, so not let the bullet pass through. But you also want to sort of take the impact and dissipate it. Like you want to sort of take that energy that comes from the impact and somehow absorb it, right? And liquids are good at sort of dissipating energy. In fact, so this is the classic example, right? So if you think about an elastic solid like a rubber, elasticity, they store energy. Elastic materials just store energy. So if I take a rubber band and I stretch it, I've stored elastic energy in it, and it stays there. If I come back after 500 years, that elastic energy is still there, assuming the rubber band is perfect. And I let it go, it remembers where it was, and it releases all that energy. Not so with the liquid. So with elastic materials, you can put in energy, nothing, it just gets stored and it is released. Whereas, you take a tub of water and you put energy in it by just maybe swirling the water around. Over some period of time, the water stops moving around because it's dissipated all the energy you put in. So viscosity is dissipated. Like, it'll take whatever energy you put in and dissipate that eventually as heat. And the more viscous it is, the better it is at dissipating energy. And so you can imagine designing, like either bulletproof vest or some sort of armor, which is good at both things. So you want it to be hard so that it can sort of resist direct impact, but it has enough viscosity so that it can, in fact, there are materials that will strain harden. So if you try to they get harder when you try to pierce them. Or what's a classic example? I mean, there's an example from my area of research, which I don't know if that's helpful, but I'll try. And then I'll give you maybe a more common example. Actually, let's start with a more common example. So if you actually go to a beach, right? And then if you try sticking your foot inside the sand, close to where the water sort of comes in, and you try to move it around, you'll notice that if you try to move the faster you try to move your feet, the more resistance you feel. Whereas if you try to move it, like in that wet sand, if you try to do gradual movements, then the liquidy sand offers like a smaller resistance. So the viscosity increases with. I think a similar thing also happens with quicksand. I mean, maybe this is just quicksand. So I've never been trapped in quicksand, but I think the advice is don't try to like flap your arms. Try to sort of like smoothly glide your way out, because that way you're facing a lower viscosity, and so you want. Well, in a bulletproof material, you want strain hardening. So you want the material to harden. You want it to behave like quicksand in some ways. Yeah.
Quicksand is one of those things. Like growing up and watching cartoons, I thought quicksand was going to be a much bigger concern in my life than it was.
That's right.
It was that and like stop, drop, and roll. Like everyone's on fire all the time. Like it's good advice, but you just never.
Have you ever seen quicksand? I actually don't think I don't know if I've ever seen quicksand.
And I've seen people like it's not that deep. It doesn't like pull people's full bodies in. Like your legs might get stuck, but like you're gonna get out eventually. So but we were led to believe many things. All right, so it's 9:30. Do you want to keep playing this? Do you want to switch to racing? Do you want to switch to we can do Fall Guys? What do you want to try?
Let's do the racing game. Maybe.
Let's do the racing game. All right, we're gonna change it up, ladies and gentlemen.
Pure dimensions.
Pure dimensions. All right. Transition to the head so you don't have to look at the Xbox screen. So as soon as that lights up with the game, you can press the green button. Where all the sand traps, exactly, or led to believe all these would be a problem.
That's right.
Also, I was terrified of the Bermuda Triangle as a kid. Are you familiar with it?
I know. I heard the Bermuda Triangle, right? Yeah, and I feel like was there a movie called the Bermuda Triangle?
But it was just like this I don't know, ancient tale and things like that.
Yeah, of planes disappearing and never coming back.
Yeah, exactly.
And we live next to the Bermuda Triangle.
Exactly.
Most of our planes probably go through Bermuda Triangle.
All right, ladies and gentlemen, we are switching over to Pocket Bike Racer, which is another one of the Burger King games. There you can kind of see the artwork right there. Yeah, it's a racing game. So single player, free play. So go to the right. Pick a map, pick a race. Contra, thank you for joining us. It's been a pleasure. Yeah, swing back anytime. It's great to have you on. We need to have a music theorist on again. I really like learning from people that are way outside of my domain of expertise. Sachin and I serve on like similar advising committees because we're close enough. But yeah, when we get experts outside of the domain, it's eye-opening, right?
Yeah.
Like how you align roads in a city. I would have never thought of that.
Yeah.
Like same thing with archaeology. Have we seen Sneak King yet? Not Derry wants to see Sneak King. We'll see if we have time for some Sneak King. We might get to it a little bit later. It's a terrible, oh, non-dairy, you're bringing out the worst in us. Is BK the sponsor tonight? No, but it should be. It absolutely should be. We should be eating Big Macs.
No, not Big Macs.
No, sorry. Not Big Macs.
Whoppers?
Whoppers. Yeah, sorry. Oh, man, now we lost our sponsorship. This stream brought to you by Burger King. I don't know, Lori. This is just the game we play. In fact, I had my group party last week, and I set this up for my students to play because it's a 4-player game. So trigger is the forward.
Oh,
there you
right.
go.
And then jump was?
There's no jump on this one. It's just steering with the joystick. Okay. Yep, there you go. So yeah, racing as the king. This is just a racing game. Nothing too detailed about it, except for the maps are terrible on this. It's really hard to find which way you're going. So now you're going backwards. Turn around. All right. So we have a question. Anka Music wants to know, I think the field of rheology includes these studies. Correct me if I'm wrong. Well, you are in luck, Anka, because Sachin is one of the world's foremost experts on modeling rheological behaviors via various different computational methods. So yeah, it's rheology related. Sachin, can you explain rheology? Like the measurement itself is intriguing.
So there's lots of different ways of doing rheology. So the way I explain rheology is it's a scientific study of how materials respond when they are deformed. So when you take any material and you deform it, so it doesn't like to do that, so it generates forces which resist that deformation, and a rheological measurement tries to measure these forces in the form of stresses. So this is one way of setting up a rheological measurement. So you can take a material, you can strain. In the jargon, it's called strain. So essentially, you deform, and then using something called a rheometer, you measure the stresses that are generated, and you plot them, and that tells you something about sort of these viscoelastic properties. But you could run that in reverse, as in you take a material and you apply a fixed force, and you try and look at how much it deforms. So either you apply the force and you measure the deformation, or you apply the deformation and you measure the force, and both of them give you a window into essentially these viscoelastic properties. And in fact, there's something called linear viscoelasticity, which is this limit of small deformation. So again, you're close to equilibrium, and then if you're close to equilibrium, it doesn't matter what experiment you perform. All experiments give you the same information. In fact, there's something called the Boltzmann superposition theorem, which lets you convert any linear viscoelastic measurement. You can invent your own particular type of deformation, particular way of perturbing a material, and so long as you can measure the stresses or measure the strains, you can convert that into one answer. It's like the Lord of the Rings ring. Like there's one ring to rule them all. So it doesn't matter what experiment, it contains the same information as any other type of experiment.
Oh.
And so, I mean, there are some. So there are broadly speaking, I don't know, in linear viscoelasticity, I don't know, is this too much detail?
Maybe, I don't know. Contra, if you're into it.
Yeah. There's this famous pitch drop experiment, which the entire experiment is just, you stick like this asphalt in a in a funnel,
Yep.
and then you watch how many drops of it drop.
Or you watch it in real time and drop.
You can watch it, and I mean, it's not particularly exciting because I mean, it's an experiment that's been going on for
90 years.
90 years,
like
yeah, so probably 100 now.
Yeah.
I think probably over 100, and it's like I think it's been like 9 or 10 drops so far.
There is a link in the chat right now if you guys want to watch that experiment.
Yeah,
it's a video camera of this, and a drop falls literally every 10 to 12 years or something ridiculous.
That's right.
Like
Yeah,
that. So
and I think so. There's a camera, but I think a couple of drops have been missed.
Yeah.
So it's like, you know,
and you can watch the
You had
YouTube
one
videos
job.
of one of the exactly. Well, the guy that started the experiment never got to see one drop.
That's
So
right. I think I'm kind of stuck.
So try this. Should get you forward. Trigger gets you forward. Sorry, we're distracted a little bit. Drop watch party. Let's do it. Let's do a live stream of the pitch drop experiment. I'm gonna binge it. That's amazing. Yeah, rheology is a really cool measurement. That's man, my favorite version of that measurement, and you guys can see my hand there, is you put your sample on top of some platform, and then you put some kind of contact on it, and this thing rotates, and it'll rotate at different frequencies, and it'll oscillate back and forth, and you can basically see the resistance of the material to that oscillation.
That's
and
right.
your frequency of oscillation tells you something about the force as well as the time it takes, so it's response time. It's just a real cool, like, temporal frequency. I don't know how you got in this camera view. Is it maybe one of the buttons? I honestly don't know how you got it, because usually you see it from behind.
That's right.
But anyway, Contra, I had 100% complete on my gamer tag, and then someone played Sneak King on my console and got one achievement. One of the speed weapons was so badly tuned that it could only be accomplished until after grinding for 4 or 5 hours. So the third game in this series is called Sneak King, and it is something else. It is weird. Maybe we should play like 15 minutes of that. But oh man, Contra, I feel bad for your completionist mentality, because that is a nightmare, and I'm sorry you tried to do that. That is terrible. Oh man, Sneak King. I just looked up the speed run for Sneak King. Let me see where it is. There it is. So the record time in any percenting Sneak King is 54 minutes and 2 seconds. That record is clearly up for the grabs. Go Haku, when do we get to NARC? We're going to get to NARC at about 10:30, we'll say. 10:30 Eastern is NARC time. 30 minutes seems reasonable. I think last time, I looked up your time, it was like 36 minutes last time. So you'll be faster this time, right?
Okay, there's no guarantee.
We'll try.
I like your optimism that I think is unfounded.
Oh. Yeah, try some of the other buttons. We'll see if we can get you back to the other view, because this is a nightmare. No,
Okay, I am B for back. No. Oh, let me try that again. Maybe I
didn't know you could change views. Contra believes. Contra, if this is your first time on stream, at the end of every stream, I have my guests, and again, it's every other week, or every 2 weeks I have a guest on. I make them close the night with a game called NARC. It's a bargain bin game for the Nintendo Entertainment System. It is absolutely terrible, but Sachin, you're going to win the war on drugs, so for the second time, totally worth it. So yeah, we can put bets on that. Gohaku, thank you for keeping us on point. We definitely need to keep our NARC in mind. Mr. Big awaits Sachin's interventions. All right, we should do another prediction. Which one of these three do you want? We got those 3 left.
Which one do you think? Maybe
it's
this
up
one?
to you.
Yeah, that's that.
This is an interesting nomenclature question. All right, everyone, have your standard internet unit points ready for this next prediction. We're going to pop a prediction up there. You're going to have 2 minutes to answer this question related to polymer materials, natural polymer materials. And so we are going to ask a question about natural polymers in cell plant walls. Is it cellulose or celluloid that adds the infrastructure? Thank you. That name is in Chinese, so I can't pronounce it, but thank you for following us. Enjoy your standard internet units. Use them to predict on this question. Natural polymers in plant cell walls. Is it cellulose, or celluloid? And this gives the primary infrastructure behind plant materials. So answer your question now. Is it cellulose or celluloid? Click that predict button. Ooh, good question from Gohaku. Why can't polymers be recycled?
Oh, good.
At least recycled easily and efficiently. And I think the first answer is that's not true for all polymers.
That's right. That's right.
It depends on the type of polymer. So of the polymers that can't be recycled easily, what's going on with those?
Yeah, so it's kind of so broadly speaking, there's two kinds of. Is there a jump?
No jump.
Okay.
Thanks. Oh no.
Okay.
Yeah, I think going up the top corner is the way to do it.
Okay.
All right. So why can't some polymers be recycled
Yeah.
easily?
So there's broadly speaking two classes of polymers. There are those that are called thermoplastics, which are like which are the polymers that your stuff like milk cartons and plastic bottles and stuff like that are made of, and those actually are recyclable because they're made from polymers that are not cross-linked, so they don't look like slime or rubber. So they're just individual chains that are tangled up together, and they get all their properties from the fact that they are tangled up. And those polymers, if you heat them enough, you can reprocess them into different shapes. So those are recyclable.
Or you can dissolve them in solvents.
Yeah, you could do that too. You could do that too.
Like add acetone on styrofoam, dissolved.
That's right.
Does that bring cross links, or that just dissolves the chains?
So you don't even have to. I mean, you don't have to dissolve them necessarily. You just make them. If you lower their viscosity, you can just reprocess them, right? Like you have material and you can just make new shapes with it, right? And so that's, on the other hand, there is this other class of plastics called thermosets, which are cross-linked polymers. And what you get with thermosets, so thermosets would, make maybe like the casing of this, something like car tires are a classic example of a thermoset because they are cross-linked. And cross-linked polymers have great properties, so, with temperature, they don't lose their mechanical strength or integrity with temperature. They have much better chemical resistance, etc. So in general, they have sort of superior properties. So, they can...
I'll get you back in the game.
Yeah. I have trouble double
multitasking, not Sachin's strength.
Yeah. So it's... Okay, I'm going to try and turn.
Yeah. Pull forward.
Okay.
It's the right trigger. Yeah, there you go. Oh, there you go. Up the ramp.
Okay.
This is a non-trivial course.
Yeah, I should pick something simple. Right?
No worries. We'll probably do some Sneak King because Contra has requested it. Contra and who else? We might as well do a little bit of Sneak King because this stream brought to you by Burger King.
So again, sorry. So these thermosets are next to impossible to recycle, and the only way, the only way we can do something about it is to maybe reuse them in some application. But you can't recycle them in the usual sense. Yeah. How do I know where to go? Oh, okay. I see those arrows there.
Yeah. This is a hard map.
Has this always been my bike, or have I been downgraded?
No, I think this is it.
Okay. I mean, it's a pretty lousy bike for a king,
For the king.
The king.
The Burger King. All right, anyone just joining us, Ask a Scientist Gaming, mediocre gameplay expert science. Our guest today is Sachin Shanbhag, who's an expert in soft materials and modeling those materials with various different methodologies, and describing rheological behaviors in materials, polymers, natural polymers, synthetic polymers, whatever it might be. Sachin is interested in all those things. So yeah, if you guys have questions, ask those. He's also in the Department of Scientific Computing at Florida State University. So he does a lot of programming. In particular, he's talking about doing Python as well as C++. He's happy to talk about anything. If you guys have any questions, throw them in chat right now. We'll play this game for another, I don't know, 15-20 minutes. We'll try a little bit of Sneak King just to see how it goes, and then we'll close the night out with a little bit of NARC, but we'll answer science questions along the way. In fact, you guys can distract Sachin and make him terrible at games. Non-dairy neutrino. What's the time complexity / runtime for soft body modeling? Like, what are the parameters that scale
with particle? That's a great question, and it sort of depends upon what kind of calculation you're doing. In general, things scale. I mean, it sort of depends. Right? So if you're doing something called molecular dynamics, so you're representing everything with like atoms or molecules or something coarse-grained, then typically it will be order n squared, right? You can make it n log n using certain tricks, but with a big coefficient. If you have, yeah, so I'll leave it there. So it's somewhere between n log n and n squared, where n is the number of sort of particles in your system, is how something like molecular dynamics would scale. Of course, you don't have to do only molecular dynamics. There are all sorts of fancy techniques where you can, there are these field type methods which have much better scaling, and there you don't. Okay, let me just get this part right.
You got it.
Okay. Yeah. So where I mean, they generally solve slightly. Oops, wrong way. I'm pretty good at this.
So go left, turn that way,
no,
and you'll turn up the hill. There's like a ramp there. That hill. Did you see it to the left there? That like
I missed
pile?
it again.
Yep.
Okay.
Oh yeah, we didn't answer our prediction. Natural polymers and plant cell walls. Is it cellulose or celluloid? Sachin, what's the answer?
Oh, so the answer is cellulose. Right?
Cellulose. So 92%, at least the gambling percentages, got that question right.
Oh, that's good.
A few dark horse votes. So most people knew it was cellulose, which it's underappreciated. There are natural polymers like
right,
cellulose, but not just that, but like amino acid sequences that make proteins. Those are polymers.
That's
DNA is a polymer.
That's
just
right.
monomer units that compile together to give unique properties of the bulk. Yeah, polymers in natural systems. Is there any follow-up you want to say on the difference between cellulose?
Yeah, so I thought the reason I brought that up is because I mean the question would be what is celluloid then? And celluloid was used to make these films to record movies on, right? So celluloid films, and in fact. If I'm not mistaken, they were like a early 19th century, 20th century, late 19th century, early 20th century type of invention.
Yep.
And the problem with celluloid films was they would catch fire, right? I mean, that's
well, correct me if I'm wrong, but celluloid is like a nitrocellulose plus a cutting agent.
That's right.
Like a salt of some kind.
That's right. So that you already know it's right. So it's not a good mixture, right?
Yeah.
So from a flammability standpoint.
Gun cotton, basically.
That's right. Yeah. But the sort of the interesting thing is, I mean, I don't know what these are called, but like we still use the word films to describe movies, and that is a remnant of the fact that these movies used to be stored on films
which is also a problem in the movie archiving industry, right? Because these materials have a lifetime, right? These celluloid materials decompose over time because ultimately they're molecules, and as they heat up, as they get oxygen, they just decompose, and with it the images are lost and the films are lost forever. So
I mean, that's just archiving material is just kind of an interesting problem, right? So because like everything eventually degrades, like everything. Even the materials we have today are not like foolproof in that sense, right?
Magnetic hard drives.
Yeah, magnetic hard drive. I don't know if you like. I didn't know this. I heard like you listen to Radio Labs. So it's like a podcast, very public.
I'm familiar. I don't regularly listen, but I probably should.
But so they had this episode on. So I forget some small X Soviet republic. So I'm thinking it's something like Estonia or like one of those republics, and they have it's probably Estonia because I think it anyway. So they have they vote for their elections electronically. I think they vote on the phone or something like that. And there was this one candidate who got like who wasn't expected to do well, and he got like a strange number of votes. And people initially thought it was foul play, maybe it was interference, foreign powers, blah blah, blah, etc., etc. And then when they looked closely, okay, I'm misremembering all the details, so you should probably go check. But the interesting thing that happened was like one of the bits got flipped because of a stray cosmic ray, and apparently this is something that is known to people who work with computers at like at high altitudes, because cosmic rays are more prevalent there, and it'll occasionally knock off like a magnetic spin from this state to that, and typically it's small enough and there is enough sort of coherence in the sort of other structures that you can but occasionally it's a problem, and it's a problem the higher you go. So if you ever sort of go to Mars or spend, I don't know, anyway, so like I didn't know this, but when I learned, I thought this was kind of interesting that like just like celluloid is fragile, so are our magnetic disks, and in fact, I mean, if there's one of those, what are those like solar bursts? I forget what those
the solar flares.
Yes, solar flares. I mean, if a big one hits, I mean, I don't know, I'm screwed.
Mr. Adventure said it was something like 1048 votes.
That's right.
An increment of 8,
yeah,
so
maybe 1024.
Or 1024. Yeah. Non-dairy neutrino followed up. Yep, cosmic ray bit flips. I think there was an instance in Super Mario 64 speedrunning as well, where someone's speedrunning a video game, and there was an instant glitch that like is not reproducible, but it changed the outcomes of the game.
Positively or negatively?
Yeah, I think it was positively. Like it cut time out of the race, if I remember correctly. But yeah, it's one of those instances that are just crazy unlikely.
Yeah.
All right, Gohaku has a question, but we're going to put up a prediction because it's related to this one. Are there natural polymers that are strong enough for asphalt? And so we have an asphalt-related prediction, so we're going to put that up there right now, actually.
Yeah.
And so before answering your question, Gohaku, and I'll promise we'll get back to it, we're going to pop up this prediction. You guys have 2 minutes to answer this prediction. Use your standard internet units. Speaking of which, we just had a follow. I'll get back to you in a second. But yeah, the question is, when you put recycled tires in asphalt, does it improve it improves the durability? Is that true or is that false? And so durability in this case means lifetime of the material, presumably. It just lasts longer if you put rubber tires in it. Yeah, I like a lot of these questions because they could go either way. You can envision a scenario where it does make it more durable and one where it makes it less durable. Like, does the polymer degrade quicker? But the question for you guys, recycled tires in asphalt improves their durability, true or false? And so, yeah, put your predictions in there right now. Yeah, use your standard internet units. Speaking of which, G-Blitz Gaming, thank you for the follow. Thank you for joining us. If you have questions for Sachin, put them in chat. But use your internet points right now to make a prediction about the recycled tires and asphalt and whether it improves the durability. I know there are certain scenarios where we do put recycled tires, but I don't necessarily know why, if that's just the durability or is some other reason why one would want to do that. You guys are putting your prediction in there now. Note, you can't cheat. You're on Ask a Scientist Gaming honor policy, so be honest in your answers. Don't use Google, don't use ChatGPT. Use your intellectual knowledge and what you've learned about Sachin and his gameplay to answer this question.
Not gonna help.
It's okay. It's a fun question, a fun prediction. I'm curious how often they do this, or if they still do this, or they abandon it for various reasons. It's a lot of convoluting things. Man, I love that. Just like a random neutrino completely screwing up one bit, and it just changes everything. Because I don't know if you're familiar with speedrunning, but the idea of optimizing a game so much that you play it perfectly, and then something like that happens and you can't reproduce it. It just happens once in a billion tries. And it just changes everything.
Yeah.
Ooh, Gohaku's follow-up. All right, we will get to that one as well. 5 seconds left. All right, Sachin, what's the answer?
Yeah.
Recycled tires and
True.
asphalt
Yeah,
improve
that's
durability. True. Most of the audience knew that. We got 91% return on true. So
Yeah.
why do they add recycled tires? What does it do?
So it's one of those. So they use recycled rubber crumbs. So I mean they make crumbs out of rubber, and so it helps in two different ways, right? So it solves one problem is the problem that maybe we try to answer in our the last question, which was about recycling polymers. Rubber is notoriously hard to recycle, rubber tires especially, and so you just throw them in a landfill or you set them afire. I mean those are like typical end of life fates of rubber tires. But if you can make rubber crumbs out of them and you can mix them with asphalt while you're making sort of new pavement, it gives asphalt elasticity, right? So, I mean, a common mode of failure for asphalt is a tiny crack starts, and that starts getting wider, and maybe salt water seeps in, and I mean that's how the road eventually degrades. I mean, there's a small crack, and then that opens up. Adding these rubber crumbs gives it elasticity and sort of fills in the crack. It sort of disrupts the flow of these cracks and makes it more durable. This was started as a pilot program, I think, somewhere in the late 60s, if I remember right. But now it's sort of like it's widely used pretty much in every state in the U.S. And it has also another ancillary sort of benefit other than just mechanical sort of durability. Just because just because of its viscoelastic properties, it turns out that roads made with this kind of mixture with rubber inside asphalt actually indirectly addresses noise. It's about 10 decibels quieter, and decibels, remember, is a logarithmic scale. So it's a just highways makes it far less noisy. So I mean, this is one example where it's good on all fronts. You recycle rubber, you make better pavement, and you reduce noise.
That's awesome.
Everything going through it.
I like non-dairy neutrinos answer. I guessed because it makes it squishier.
Yeah.
That's
exactly
elasticity. Right. That's definitely what I meant. Yeah. That's the technical language, but it's true.
That's right.
All right, should we play some Sneak King for the last half hour before NARC? Okay. All right, Gohaku has a question for you, though, and this is an important one. How come beer bottles are not made out of plastic?
Yeah, that's a good question. So I'll give you an answer. I'll give you a speculation. I haven't thought very deeply about this question, but when you make materials for food packaging, an important property is permeability. So what the packaging allows, allows. Well, I take that back. Like soft drinks, soda bottles do come in plastic. Okay, so I don't know if there is a technical reason why beer bottles are not made of plastic. There are some. Isn't there some?
I mean, oxygen matters a lot more for beer than it does for sodas. Permeability might be one of the reasons. I don't know.
Yeah. So oxygen from the outside coming in.
Yeah. Because if that oxidizes beer, you end up making acetic.
Like the taste would suffer.
Acetic acid. Yeah.
But that's not a problem with like
sodas. I don't think as much because oxygenation. I mean, it's carbonic acid bit. I don't know.
I don't know how much carbon dioxide. Like how different beer is with respect to carbon dioxide relative to like soft drinks. I don't know. Yeah, I don't know, but I do know like champagne bottles are made of thicker glass than wine bottles because of pressure. So I mean,
that's a force issue.
Yeah, it's directly a force issue. So it may be something like that.
Hey, all right, Sachin.
Was there like one? I feel like I've seen one beer bottle made of plastic. Like,
that's interesting.
Recently. I forget what brand that was.
All right, ladies and gentlemen, this is Sneak King. So I'm going to show Sachin just how to do this briefly. I'll do a quick walkthrough. But yeah, this is Sneak King. This is the third of the Burger King games. The stream brought to you by Burger King. Just But the way Sneak King works is you're going to sneak up on people and you're going to give them a burger.
Oh, okay.
So this is, as one of my students put it last Friday, this is the precursor to like, I don't know, Assassin's Creed or Splinter Cell or any game where you have to sneak up on people, this game walked so they could run. So, so here we are. We're going to play a little bit of Sneak King. And so I'm going to show you briefly. So you're the king. You're going to walk around. You're going to select some missions because this is an open world game. So you have two different joysticks. The right one does the camera, which is inverted for some reason. And then the left one does the steering. And so what you're going to do is go around, sneak up on him. So that guy has a burger on the mind. So what you want to do is give him a burger. So you're going to sneak up behind him. And as soon as it says A, hit A. Then you're going to get a flourish. And you're going to give him a burger.
Okay. And you can mess this up if you go too fast?
If they see you, if you're in that blue path, they'll see you.
Okay.
And so you want to go, there's a burger over there. So you're going to sneak towards the burger.
Oops, not from the front, right?
Yep. So you're going to get behind them. Try not to get caught in the blue path. Ladies and gentlemen, this is
you don't want to be in the blue path. Okay.
Yep, the blue path is like their line of sight. So go right.
Okay.
And then the camera is the other joystick. So you want to... And then get close, hit A. Oh, and she got too hungry.
Oh, that happens too. Okay.
They're gonna pass out if you don't.
She had something on her.
Yep.
I'm so bad.
So yeah, look around with the other joystick. You could find other people with burgers over their heads. So, ladies and gentlemen, you demanded it. Here it is. This is Sneak King, the third of the Burger King game. This reminds me of the 100 free hours of AOL you got from a Captain Crunch box. How dare you? I paid $4 for each one of these games. There you go.
Oh, wow.
That's it. This is the entire game. And the speed run, the best player in the world is beating this game in 54 minutes.
How many of these people are hungry? You know? Like how many? I
think you have to do 3 of them on this particular challenge.
Okay.
All right, if I missed any questions, I apologize. Recycled tires and asphalt, that's pretty fun.
No.
I wonder if they did that just like as a... If it was thought through or it was just like, we have a bunch of rubber, we got to do something with it, let's try it.
Yeah.
Then they patented it. Non-Dairy had a comment earlier. Molecular mechanics is already end of the 2. Do you use ab initio methods like Hartree-Fock self-consistent field iteration? Furthermore, how accurate do you go with these EE correlations? Coupled cluster density functional?
Oh, good question. So I actually abstract away from electrons. So I, like the smallest unit of matter that I will consider is typically an atom. So so electrons are just approximated in some form in what is called a force field. Right? So how 2 atoms talk to each other. So I don't do any electron, so nothing with electrons in it. So so no Hartree-Fock, no. This is all a question of time scale, right? So if you so electrons move on much faster time scales, and so if you want to do a calculation, a dynamic calculation with electrons, you can never get that far in time. And like I told you, like a lot of these materials have relaxation times of the order of seconds or tens of seconds or hours even. I mean, you saw like the asphalt over the asphalt in the pitch drop experiment. I mean, that has a relaxation time of the order of decades in years. And so clearly you can't use. I mean, no, I shouldn't say you can't use. It would take you forever if you resolve electrons and try to sort of predict the rheology of something like asphalt. It would just take you forever. It's like I don't know. There's this essay that I read. I don't know if you've read this, Ken, but there's this essay in, I want to say, either Science or Nature, sometime in the 70s, called "More is Different," which is effectively. I mean, like physicists tend to think that physics is like the is like the everything is physics. Like all of chemistry they think is physics because, right? And if you write down the Schrodinger equation, then there is nothing in chemistry. You just solve it's a computational problem. If you could solve the Schrodinger problem, you wouldn't have to do any chemistry in the lab.
Yeah.
You could just predict everything, right?
Yeah.
But when lots of atoms come together, something different happens. I mean, in principle, you could solve the Schrodinger equation, but there is that is not the appropriate level at which you can do, let's say, something organic chemistry or polymer chemistry. I mean,
Yeah.
and then biology, which is maybe, there are lots of, so sometimes you have to worry at the level of an animal or ecosystems, and you can't worry about atoms when you're talking about ecosystems, and you can't definitely worry about electrons.
Yeah.
So in a certain sense, you could predict the fate of an ecosystem by solving like a huge system of Schrodinger equations, but it's pointless because it reminds me of that answer from the Hitchhiker's Guide, right? So you could come up with an answer, but it would mean nothing because the answer is not expressed in terms of primitives that you understand, right? Like you don't like what constitutes for an explanation in biology is not a wave function. Like even if you could describe it quantitatively, that wouldn't do any.
What do you do with that?
Yeah, any job of explaining stuff. And then like same thing, biology becomes like just psychology, when lots of stuff happens, just the science of mind, or sociology, like lots of individuals get together. I just think like, when there are interactions between lots of things, even if you understand the individual, the collective just brings these emergent phenomena into play that sometimes you want to just start thinking at a different level, starting with different primitives.
Non-Darius counterpoint. You can't tell me what to do. If I can talk about a wave function of the universe, I can talk about a Schrodinger equation of a rabbit.
That's right. You could.
Schrodinger, the wave function of a rabbit. My favorite is that if you shoot enough rabbits at a 2 slit that's the appropriate size, you will get a destructive pattern from wave function of a rabbit. Theoretically.
Yeah, you would. Yeah. Yeah.
You can't tell me what to do. Yeah, but what's its eye color? Like,
yeah.
I mean, so it sounded like you were alluding to as well, even if you solve a solution exactly, there are emergent phenomena that happen that aren't necessarily accounted for by, fundamental physical principles. The one I give Eugene a hard time about is like he does, CI singles, right? These very fundamental calculations. Yeah. You do that for a car, it still won't drive because there's no gravity, right? Like there's unaccounted for forces that aren't there. Yeah, we don't have a grand unified theory of physics. Until we do, there's different levels of abstraction which you model systems, and if you don't, you can't describe them accurately. So I really appreciate that. That's a fun article.
And in fact, so it's so in my department, there's lots of people who do this machine learning stuff, right? And I kind of was a machine learning skeptic as applied to science for the longest time. I'm still skeptical, but I'm less of a skeptic than I was, some time earlier, because maybe this was too clever by half or whatever the expression is, right? So I always thought, maybe the machine learns, but unless it can explain, what it has learned to me in terms of things I can understand, and what I understand is conservation laws and sort of some principles, etc. Then the machine having learned doesn't mean I have learned anything new. Like just being able to predict something isn't sufficient. I don't know. Are you familiar with like computer proofs of mathematical theorems? So like it's the same level of unsatisfactoriness that I feel when you have
that's an empiricism, right? It's just like so fit it with the straight line,
right? So you have an explanation. I don't know whether you have you have a prediction, you have you have a description, but maybe you don't have an explanation, or something like that.
But is that good enough?
Yeah, like are you satisfied? I think the question is, are you satisfied?
Yeah.
Right. I mean, if you want to design a self-driving car, you probably don't care what model has been learned, or maybe you do care, right? But I guess you care less about that, as long as it is, it makes perfect predictions. I think that would be perfectly fine. Oops, I
guess that's one of those boundaries between fundamental knowledge and applied, right? Like if it's applied and it works, do we care how? Do we care if the black box did it?
So where do you fall?
It depends on what application we're talking about, right?
Yeah.
Like if I just want to know a behavioral pattern, it's awesome, right? It predicts. Here's the two variables that correlate. Are they causation? Do I care? As long as I can change variable X and get outcome Y, I don't care.
Yeah.
A lot of the time. So
that's right. Yeah.
We'll apply machine learning to the perfect city we built.
That's it. Yeah. And yeah, I mean, we shouldn't dismiss it. I think maybe if you can predict it, then you could run experiments on the prediction and maybe learn something that way. You know, like
that's what I like about it. Like, I mean, ultimately, machine learning, you give a spreadsheet of data and then create some kind of polynomial that has two variables that are closely related. It doesn't claim causation or correlation, but at least you've narrowed it down to two things you can measure. And if you can do that, change one and see how the other affects, that's experiment. So yeah, I'm of that camp. It's a useful tool, but it doesn't necessarily give you a scientific answer.
Yeah, I have warmed up a little bit. You know, I'm just immersed in an environment where everybody is like super excited. It's like some of it just eventually rubs off.
So like every third seminar you see is machine learning and AI.
Machine learning, and all the students want to do. So you know,
but they're not wrong, right? That's a huge job market.
I think it is. You know, again, this is the same thing. So I feel like it's my bias, or my, you know.
The old man, get off my lawn again.
Yeah, I think it's exactly that.
At least you're reflective about that. Like you're thinking about is it me or are the kids wrong? Like,
yeah, I wasn't always like this. I think I was more sure about myself. Yeah.
Anka Music, people seem a lot interested in predictions, by the way, as all the banks and insurance companies want to predict the future. Also, stock market exchanges, like they don't care why it changes the way it does. They just want to predict.
Yeah,
they want to respond instantly. So yeah.
So I mean, there's this there's this company called Renaissance Technologies. I think it's one of the most successful hedge funds ever. Like they don't even accept sort of outside money. So if you wanted to give them your money, they wouldn't take it. Like it's all internal. And they have I forget exactly, but their returns are like 30% for like 30 or 40 years. So I mean, you could with that kind of, and the interesting thing about Renaissance is that it was founded by a person who was previously the chair of the math department at Syracuse, I want to say. So it was like a mathematician. Yeah. And what they do is do precisely that. I mean, even before machine learning was a big thing, they would just try to identify random patterns which seem to be going together and make like short-term bets on the pattern, even if the pattern didn't make any sort of causal sense. You know, you just bet that will, you know, the trend will persist. I think the game's gotten a little harder now because, you know, like lots more people are doing it. Yeah, and so there's too many more eyes.
And the programs are trading before any human can make a decision, right? It's instantaneous. Yeah. And so you have computer fighting computer. I heard that like a majority of physics graduates don't go into physics for a job. They go into like economics. They end up doing stock trading, and programming, things like that.
You know, like the need for speed is so high. You've probably heard of this. Like people paid to have straight line cables to the exchange, from, you know, like from Chicago, just because light, because, you know, like it's like the speed of light is not fast enough.
It's 1 nanosecond per foot.
That's enough, you know.
Cut out 10 feet and you're 10 nanoseconds faster. Go Haku. Wendy's has dynamic pricing on their menus now. They backed off on that, right? They had proposed that. Had you heard this?
So depending upon the time of the day?
Yeah, time of day and number of people like lined up, the price would change. Like kind of like what like Uber and Lyft.
I don't know what
I don't know what you did. Try another button. It's like first person mask view. I should have really played this game again before you played. Can you walk around? Are you in a, maybe hit Y? We'll get you out of.
Oh, okay.
There we go. You're like hiding behind a tree or something. Yeah, but I think Wendy's backed off on that because there was a lot of backlash of flux pricing. Like with Uber, it kind of makes sense because you get to see the price before you decide something. But if you pull to a Wendy's drive-through and it changes depending on if you're the fourth car or the first car, like, holy crap, that's terrible. Nobody should have to put up with that. All right, we should do one more prediction at 10:17. Which one do you want to do? Actually, we only have one left. Never mind.
Oh, that's good.
Because we're not going to do it during NARC, because NARC, you got to focus. You got to time.
As you notice, my performance doesn't change whether I'm...
Imagine people scaring off other customers just to lower the prices. Exactly. Or just go there at 3 a.m. and... You can play that game too. Take that, Wendy's. Well, machine learning this. All right, ladies and gentlemen, we're going to do our final prediction of the night. Final prediction, at least science related, of the questions that Sachin has written for us. So this is a question about short chain versus long chain polymers. Polymers being long extended chain of monomer units that you repeat over and over again. You can make them long, you can make them short, depending on what property you have. So this is a property related question. And so the stronger, more flexible polymer has longer chains or shorter chains. And so if you're going to make a stronger and more flexible polymer, do you want to make those chains long or do you want to make those chains short? So this assumes consistent cross-link density or something like that.
The same polymer, the same kind of chemistry.
Just slightly different lengths. Long chain versus short chain. Which one gives you the stronger, more flexible polymer? That's another one of those questions. Is like intuitively I can think one way, but what I envision might be entirely wrong. So I look forward to seeing
these have no cross-links. Okay, so no cross-links in them.
Yep.
Just plain polymer.
Just plain polymer. Long chains or short chains? If you're going to design a strong, more flexible polymer, do you want shorter equals covalent bonds? No, we're talking about covalent polymer chains. You can either make that chain like 100 repeating units or you can make it 10 repeating units. So 10 being the short, 100 being the long. Do you want those chains longer or shorter if you want to make a stronger, more flexible polymer? That's an intriguing question. Oh, so that bar that comes up at the end, so when you hit A, if you hit A again, it gives you different, it's called different levels of flourish. So you want to hit A a second time when the bar is at the top.
Okay,
Sorry, I didn't coach you through that. I apologize.
Yeah, sure.
All right, you guys have about 30 seconds left. Long chains versus short chains. Which one's going to give you the stronger, more flexible polymer? Put your predictions in there now. If you're not clicking follow, click the follow button. Get your 300 standard internet units. You have 15 seconds to gamble, but follow us. You'll get notifications about future streams, which we are excited about having. I got to figure out the summer schedule. Summer is a battle.
Yeah.
Getting people to come. What's great?
Are you here these entire summer?
Mostly. I'll be in Lisbon for 1 week, and then I have a Gordon conference. Are you familiar with that?
Yeah, I know. So where are you going?
It's northeast, but I do the Gordon donor acceptor, electron donor acceptor conference, and then Gordon photo camps.
Those are fun.
I like Gordon's a lot. Yeah. I really enjoy those. All right, Sachin, what's the answer?
So the answer
stronger and more flexible polymer has long chains or short chains?
The answer is long chains. And so the reason it's long chains is because long chains get tangled up. They form what are called entanglements. And this is, you probably, you can intuitively think why this is the case. If you look at spaghetti and SpaghettiOs, right? So if you have if you like break your spaghetti into sort of short segments and you cook it, you can easily sort of move your fork through it. It's not entangled. Whereas the long, if you have long spaghetti, it gets all tangled up. Same thing with hair, right? I mean, I have 2 daughters, and my constant complaint is cut your hair, because
I don't want to deal
long
with it.
hair gets tangled up, right? And then it's and same thing with garden hoses or whatever. I mean, short hoses don't, long hoses get tangled up. So there is this, just thermal noise and length makes things tangle up. And while that's bad when it's, when we're talking about hair, it's good from the point of view of polymers, because these entanglements act like these cross links, right? So they act as junctions that can store, can create a modulus and give the material strength. And generally, the longer the chain is, the more entanglements it has, and therefore the stronger and more flexible it is.
Mm-hmm.
Yeah.
That's one of those counterintuitive ones.
Yeah. That said, like most polymers that we use are mixtures, right? They're polydispersed. People often blend, just like alloying, right? I mean, iron is great, but if you mix it with a little bit of, I don't know, carbon to make steel,
sulfur, yeah.
you can get most of the properties and then some by sort of alloying it. And a similar thing happens with with polymers. So you can mix them, so not only do you get, let's say you want to control the glass, something called the glass transition temperature, and you want to control the modulus, and you want to control something else. What you do is you just take a bunch of different things and you blend them together, and the blend often can have superior properties to, or it can have the properties you want them to have.
All right, that closes out. That's fun. So yeah, congratulations to anyone that put long chains. Those are the more flexible and more durable or stronger polymers. Yeah, think about the noodles entangling with each other.
Yeah.
All right, we missed a question from Gohaku from a while ago, and the question was, what kind of polymers are used in 3D printing, and can they be recycled?
Can they be recycled? Actually, I don't know the answer to the second question.
What's the main one? LPA, is that the...
Yeah. But these days, I think you could do 3D printing with like most stuff, right?
So LPA is a solvent-based, partially fluorinated polymer used for protecting leathers and polymers. Is that not? PLA, there we go. PLA is the one. PLA.
Lactic acid?
PLA is...
Yeah, PLA. Polylactic
It's a thermoplastic, polylactic acid. Biodegradable,
I know that it is
compostable.
Yeah.
Compostable, that's fun.
Yeah, so it's PLA, like PLA, and its cousin PLGA is used to make surgical sutures, right? So like they will biodegrade relatively easily.
Yeah, that's interesting.
The
Just
PLA,
hydrolysis.
I didn't know it was used in 3D printing, because
PET.
PLA doesn't find too much application in other. PETG, is that the...
Yeah, that's the other.
It's a good question.
Polyethylene terephthalate glycol.
Gee.
Terabella. I bet that one's less degradable. That's a thermoplastic.
Yeah. And I guess recycled is different from biodegradable, right? So sometimes you don't want polymers to biodegrade. Right?
Yeah.
I mean, you want to keep something in a container. You hope... Or like the cellophane, like this celluloid film, right? You don't want it to degrade because you want to store stuff on it. So sometimes, but it would be nice if you could recycle it, because recycling happens on your timetable, whereas degradation often happens on, on somebody else's timetable. But that's an interesting
ABS was the one we were avoiding back then. That was a different type of polymer. ABS.
ABS isn't that like butylstyrene? It's the stuff that goes into like cars.
Yeah.
Yeah.
Acronitrile butadiene styrene.
Like it's used everywhere.
Yeah. Another thermoplastic. All right, Huggy Beer has requested a flactoid. That's perfect timing because we should switch over to NARC. So if you want to drop a knowledge bomb on Huggy Beer, welcome back to the stream. Thank you for joining us. You just caught the tail end of Sneak King, but you're here in time for NARC. It is time for some NARC. So, Sachin, if you want to drop a knowledge bomb on the audience, I'm going to change up the screens and we'll switch to NARC. All right.
I'm still looking. Yeah. So my factoid, this is about blood, and so blood, human blood, or actually any other blood, is also a non-Newtonian fluid, or a complex fluid, or soft matter. I mean, all the same things, and it has super interesting rheological properties. And just from a evolutionary standpoint, it has had to satisfy two different properties in two different situations. So one is you want the blood to be thin enough so that it can flow in the thinnest of capillaries, And so you want it to have low viscosity. And then, like occasionally when you get hurt, you don't want the blood to you don't want to bleed endlessly. So you want the blood to thicken and, so that, there can be wound healing and stuff like that. And so you want it to be thick when it is not flowing. Right? So you want it to feel like honey when it's not flowing, and you want it to feel like air when it is, like low viscosity when it's flowing. And blood does both these things, right? Because it's an example of something called a shear thinning material. So this is kind of in some ways, the opposite of quicksand, right? So a shear thinning material, the viscosity of a shear thinning material goes down the more you shear it, or the more it flows. And so when it's sort of flowing fast in your capillaries, it effectively feels like water. And when it stops flowing, so essentially you have a wound and there's blood that's pooling on the surface of your skin. So there's no flow, basically. It has higher viscosity, and it essentially thickens. It feels like, eventually it'll feel like honey. I mean, it's sort of like a higher viscosity, maybe not the viscosity of honey. And another sort of maybe common material that has the same property is ketchup. And it's sort of interesting that ketchup sometimes used as a substitute for blood, right? But ketchup, if you notice, sort of in a bottle, it's kind of hard, but when you squirt it, it shoots out really fast. So it shear thins. Effective viscosity goes down when you squirt it. So when it's flowing, it has a lower viscosity. So that, there's lots of, so shear thinning is a property of viscoelastic materials, which enables them to have sort of these dual two faces.
So Huggy Beer's follow-up, can we put it on a speaker and make blood dance like non-Newtonian fluid on Big Bang Theory? Have you seen that before?
Yeah, I think you can. Shape it. So have you had Billy Oates here?
Yeah.
So he used to do an experiment. I don't know what he did it with.
It was like a demo or something?
Yeah. So he does one with a speaker. With some kind of a material, and it does all these interesting patterns. Yeah,
that's awesome.
Yeah,
so it does do the same thing. All right, ladies and gentlemen, those of you not familiar with the stream, we close every single night by forcing my guests to play NARC. NARC is a bargain bin game for the Nintendo Entertainment System. Came out in 1980. What was the year on this one? It's 84, I think. But yeah, classic game. This is literally bargain bin. You'd walk out of Blockbuster and this would be sitting in a barrel for $2 each. A game from my childhood that I now force guests to play. And so right here I have the game. So I'm going to actually read this so Sachin is familiar with the lore. All right, you ready? You are Max Force. Your mission: bust Mr. Big and destroy his dreaded criminal empire. Seize all contraband, stolen money, illegal weapons, use rocket bombs, high-powered machine guns, apprehend all suspects, protect the innocent, punish the guilty, and stop at nothing. So our goal tonight is to win the war on drugs, and we're going to do it by playing NARC. The comment from and where was it? Huggy Beer, win all the drugs. I mean, arrest all the drugs. All right, Sachin, press start when you have a chance. And I will start the clock as soon as you land on the ground, and we will start the speed run because we time our guests.
Oh, really?
Play this, yes.
Unnecessary pressure.
You don't have to know. The clock. Clock's over here. You don't have to worry about it. Right, so we're going to win the war on drugs tonight, ladies and gentlemen. Speaking of which, the Biden administration just announced descheduling marijuana from Schedule 1 down to like Schedule 3 or something.
So should I go nice on this guy?
So in the door.
Oh, sorry. Yeah, I get it.
Yep. So on the same level as Tylenol, which will do a lot of interesting things on a federal and state level. Because, yeah, decriminalize. Stop making this a crime. But anyway, that's just my opinion. All right, grab that red card you see right there.
Oh.
So yeah, Sachin has played this before, but it was also over 2.5 years ago, so it's been a while. So keep walking, go to the door. Your goal is to go to the right and try your jumps and your...
Yeah.
Yep, through the door, go to the right. You can practice jumping and rocketing because you'll need to do that later.
Do I have a finite number of rockets? Or
no, you have infinite lives, infinite bullets, infinite rockets.
Okay,
don't lose any sleep.
Oops.
Contra, do I know you from Cooking Without Looking? That's awesome. Small world. Yeah, and if you guys have suggestions on the people we should raid, let us know. We'll raid somebody in the next 29 minutes. So we'd have to explore new people or people that are around. There's a few streamers that are on, like Science Stream. Mahoodles is on. Ryan56K, he cuts gems on stream, which is pretty cool. Gemstone Repair is apparently what he's streaming right now. But yeah, if you guys have suggestions, that'd be awesome. How's it going, Sachin? You remember this game?
It's vaguely familiar.
Yeah. There's no advantage in killing anyone other than they stop shooting you.
Oh, right. Okay.
Hit the doors, keep going right. And the audience can see your time, but you can't. No pressure. But if you guys want to ruin Sachin's speedrun, feel free to ask questions right now about polymers and soft materials and whatever you guys want to ask about. Even scientific computing, how you model systems, how you program, various different levels. He is happy to answer any questions you guys might have in the last, we'll say, 28 minutes of the stream, depending on how long it takes Sachin to beat this. So you're going to shoot the guys wearing black with bullets at close range. So yeah, hold A when they get close to you, and you'll shoot them with bullets, and one will drop a blue card. And so this is something in the speedrunning community we call RNG. There it is, blue card. Are you familiar with RNG? Have you heard that terminology?
RNG?
Yeah.
To me, it's a random number generator.
Exactly, it's shorthand.
Oh, it is?
Yeah, it's RNG, yep. And so that blue card is like a 1 in 8 drop. And so if you're doing a speed run, you basically try over and over again until you get it to drop right away. And then you have several of those instances throughout the game.
The thing I do know about RNG is there was a popular RNG called RAND-U that was used, that came pre-packaged with IBMs. That was used for the longest time, in research until like mid 1960s.
So you're gonna jump in that car with the tapping the B button. Tap a little lighter. There you go. And stay on the bottom, go to the right. That'll save you like 5 seconds. Totally worth it. Sorry, RNG came with.
Yeah, and so then the thing was, it turned out to be like not a particularly great random number generator, because it had a if you plotted three, I mean it does something like the sequence of random numbers had patterns in it, which you would expect it not to have. Yeah,
unless it's truly random.
Yeah.
But that's true for most random number generators. Very few are truly random, right? So tap jump. A little lighter. Yep, there you go. Keep going right. Loria's redeemed take a drink because it's time to drink and drive on NARC. Sachin, cheers. Thank you for joining me on a Wednesday night of finals week. Thank you all for joining us as well. It's always a pleasure. The audience makes this a really fun experience for us. The questions are great. Hopefully you guys have a drink in hand, hanging out, chilling on finals week, at least at FSU, relaxing on a Wednesday night. Hungover on a Thursday morning. Catch up on some things here. Do we know if NARC is pseudo-random number generators?
Yeah, that's
Marcinian Twister or Shiro 256 plus plus.
When was this game? When was this game invented?
84, I think.
Okay, that probably rules out a few things.
I mean, the thing about like Nintendo games is they aren't even necessarily random number generator. Some of them are just a global clock. So when you press start, it's deterministic, right? But if you're like 3 frames off, it could be a completely different outcome.
So I learned something. Like if you try to play songs on shuffle in your car, right?
So you're gonna jump in that, stay on the bottom, and then go to the top. We'll buy you some time, and then jump over this guy and keep going right. Sorry.
So what are you saying?
Random number generators.
Yeah. So the stuff in your car actually is not, the shuffle is not random because random numbers are not as random as we'd like them to be, right? So there's the streaks, there are more streaks. And then if you actually did something random, you would play the same song a lot more often rather than sort of going through your entire playlist once before. And so it's designed.
So I actually jump in and stay on the bottom the whole time.
I've never sort of learned what algorithm they use in something like a iPod. I'm dating myself.
Yeah, you're dating yourself a little with the iPod. It's not truly random.
It's not truly random. So in fact, so I remember, so you know, when I was in the university, so one of my friends, he had this, I don't know what you call them, like a bingo, but it was like a dance bingo, right? And he wanted nobody to win, the guy, until sort of like really late in the night. And so I used to use random numbers for my research, and he said, why don't you design, like, you create your own random number and make these bingo cards. Just make them so that regardless of what sequence, you know, numbers come up, nobody wins till, like, you know, like the 30th song has been played or something like that. And I said, yeah, sure, I can do that. So I generated random numbers, and I just, anytime somebody won, I would, you know, I weeded that card out. I mean, I did something intelligent. I don't remember what I did.
Going through that door right there.
Okay.
You're gonna get a silver card over here. And I wondered how many of us secretly suspected shuffle was a lie and how many felt crazy. No, it's most certainly a lie. So press up, but not too up. Left, get the silver card door. Perfect. I mean, that's so especially Spotify, they intentionally bias it, right? They match songs that have a certain tonal feel to them.
Yeah.
But also, like, if you have a random, like, new song interjection, they have financially biased incentives to play Taylor Swift more than others, right? Like, they're strategic on it. There's no question.
Don't say anything bad to Taylor Swift. My daughters love them. Love her.
I'm just saying, she's strategic and a business person, and it's clever. They pay Spotify to play more than others. Anyway, okay, let me catch up here. Lori said, in the mid-90s, NCAA random drug testing was not random either. I was never tested. The athletes they used always were selected to be tested. Yeah, that's true. Random testing is seldomly random.
Do you have to get rid of these people?
No, just go through the door, and then you're going to go to the left.
Oh,
and you have to shoot the Rambo-looking guys with bullets at close range. So that's holding A. So go keep going
not
left.
This guy.
But with bullets. There you go. Oh, not rockets. Not rockets. Hold A, and they get close. Yep. But they have to be relatively close. And it's for some unknown reason. There's some hit detection range. So kill this guy. Then turn around and bullets again when the...
Oops.
So kill him. And then Rambo will come out. You want bullets, because that's the rules, apparently. Yeah. My brother started reverse engineering this game. He's an engineer. There you go. But there's a lot of weird, like, where you have to shoot somebody and when it drops the card and all sorts of hitbox restrictions. It's crazy. All right, non-dairy. As I'm sitting here waiting for my Beamer presentation to compile, I'm curious on the longest either of you have waited for a process to finish, whether it be waiting for your LaTeX to compile, chemical reactions, or computations to run. Longest reaction I've had that I've published is 23 days, where I mix something together and let it react for 23 days. You?
Yeah, I've had a calculation run for 4 months. And when you have stuff that goes that long, you know, you want to try and sort of checkpoint. Like, checkpointing is just saving the state of the system every once in a while,
in case.
Just because there's a power, you know, like the longer you wait, the more chances there are of something going bad.
I mean, but most of your computations, they save the progress. Or is it all
so every once in a while. So, you know, I do it so that I never lose more than a day.
Okay. 4 months, though. That's a lot.
Yeah. People run longer.
The little nuances of this game seem like such an intentional troll. That's no joke, Contra. Like, the amount of time I spent deconstructing this stupid game. So I think, Sachin, it was after you played it. Like, I played it first on stream, and then I started making my guest play. You have the red card. Somebody challenged me to speedrun it, and so I did. And so for about a year, I was the world record holder.
World record! Wow.
And I figured out a glitch on the final boss, how to save about 30 seconds on the speedrun. But, like, my brother and I spent so much time trying to figure out what was causal. Like, what was predictive and what was RNG. And some of these things we just don't know how to control. And it was even, like, like you can do a tool-assisted speedrun. Have you ever heard of this? Where you basically program the computer inputs, so you can do it perfectly every single time, and even one frame changes everything. It's just it's so stupid. Yeah. What's the speedrun record? So my fastest time is 9 minutes and 7 seconds. The world record is 9 minutes and 4 seconds. And actually, the guy I beat, I told him how to beat me again, and he did. So at some point, I'll have to go back and try and beat that speedrun record of 9 minutes and 4 seconds. That's without.
Is that your, like, what's your proudest achievement? How proud were you of that achievement relative to your?
Man, I don't know. It's one of those things, like, how often do you get to say you're the best?
Yeah, no, that's why I asked. Like, I mean, it can be trivial, but if you're the world record holder, it's something trivial.
I mean, I'm the world record holder in the photon up conversion solar cell world.
Okay, that's pretty good. Yeah.
It's like, how much does that mean versus? Yeah, I don't know.
Yeah.
Sportsmanship, yes. No, if you guys are interested, I have a speedrun tutorial here. I'll pop it in chat right now. If anyone wants to beat the speedrun record, I have a tutorial to show you guys exactly how to do it. I walk through every level and every nuance that we've learned from the game. So if you guys want to beat the speedrun record, you are welcome to. It's not a very fun game to speedrun because most of it is just walking across the screen in your NARC-like saunter. But yeah, if anyone's interested, there's the YouTube link right there. If you guys want to play some NARC and beat it at the fastest human level possible, there it is. There's the information. All right, Gohaku had a question. Gohaku, sorry for the delay on answering this. Sachin, what would you say the best textbook intro to polymers? Just like talk about polymers.
Question.
So this guy, wheelchair guy, you want to hit with rockets. So what you're going to do is just clear out the guys on the screen. If you want to kill the dogs, press both buttons, A and B together, and you'll squat and shoot bullets. So hold them down together. Yep, and turn around. There you go. And then kill the guys on the screen. Wheelchair guys back, shoot them with rockets, so tap A. There you go. One. You gotta hit them 2 more times. All right, sorry. Best textbook for introducing polymers. What would be the first step one? Polymers for dummies? Is that?
Yeah. So I mean, so polymer is such a big field. I don't know. Okay. So for polymer rheology, I have a particular book in mind. There's a book called Understanding Rheology by Faith Morrison, which I think is a really nice. It's at a senior undergrad level / early grad school level, but I think it's.
There's a link in chat if you guys are interested. This stream brought to you by Amazon. Burger King and Amazon is what we sell here. All right, rockets. One more rocket on him. So this is you have to have some foundation to appreciate and understand this.
Well, not this book, but it's not a polymer book. It's more like a rheology book. It's a for polymers. I don't know if I've ever taken polymers as a class without, like I've taken a polymer physics class, but not like a. I honestly, I've never taken a polymer chemistry class.
Oh, so wow. You take Justin's class.
Yeah, maybe I'm sure.
There's a polymer. We have 2 polymer classes. Polymer synthesis and polymer characterization. So yeah, might be fun for you actually.
Yeah. So like every summer, I try to sort of pick one thing to learn.
Yeah.
So I'll pick up a textbook or like a bunch of YouTube videos. So like awesome. This is stuff that I want to learn, but like I've never take the time out to sort of study.
That's awesome.
And this summer I thought I have to learn this thing called non-linear dynamics and chaos. It's sort of tangentially related to something I want to do. And I found this book by he's a sort of a well-known guy, Steven Strogatz, and he has like a bunch of lectures on YouTube. And they're so good. Like the textbook is so good that I have to tell myself I have to stop today and sort of do my actual work. Because normally, like the way I do it, I say, okay, I'm going to just like a class. I'm just going to spend one hour, but 1 hour every day.
Yeah.
Here I have trouble sort of.
That's awesome. All right, I'm going to give you some advice. So kill the guys on the screen, and then when he comes back on, you got to tap the button a little lighter. So don't even press it down all the way, just press it down enough that it activates.
Okay.
That should give you rockets. A little too long.
Okay.
Dog, hit both buttons. Press down both buttons. Go Haku, wow, what is rheology? Rheology, so there's the definition, the study of deformation and flow of matter. It's particularly important in polymers. People regularly report rheology, stress and strain, and all those different parameters. Young's modulus, what else are the major metrics you care about with polymers?
I mean, the relaxation time, viscosity,
oh, so close.
So I'm not sure I know exactly how to get the bomb with the rockets.
Yeah, so just tap it lighter. Like, don't push the button down all the way, because you have 7 frames. So 7/10 of a second, basically.
I seem to be getting it at exactly the wrong time.
No worries, it'll happen eventually.
Just by chance.
There it is. All right, we got it. Third time.
On
You'll
the
drop a
time
gold
scale
card.
of evolution, yeah.
We talked about it. A Google time. That card right there. Then you go here. All right, ladies and gentlemen, we are on to the final stage of Mr. Big. If you have questions for Sachin, throw them in there now. Mess with him. 7-frame tap for a rocket. Yes, 7 frames. So this runs at 60 hertz, so 7/10 of a second. That's your time frame for getting a rocket versus a bullet. So this game's kind of clever in the fact that they turn 2 buttons into 4 by the press time is how it dictates whether it's a rocket or a bullet. All right, go to the top of the screen.
Okay.
And run away. Further up on top, the tongues will miss you. Yes, I have to utter the sentence, tongues will miss you every 2 weeks. So, okay, turn around, stop moving. So you're going to tap B to jump, and then A on your way down, and you're going to have a rocket hit him in the hat.
Oh.
Contra, have you played this game before? Because if not, you should. It's excellent. Find an emulator online, play some NARC, submit your speedrun, because I'm the moderator of the speedrun forum of this game. This is how you win the war on drugs, ladies and gentlemen. You have to fight the giant robotic head with rockets. Oh man, Contra. Yeah, check out the speedrun tutorial. You'll learn way more about this game and its lore than you ever wanted to. In fact, the most production I've done on any video I've ever made is the speedrun for this. And I have a video on transient absorption spectroscopy that has 14,000 views, and I spent less time on that than I did on this speedrun tutorial. So it goes. Turn around. Yeah, that was pretty close. The jump was good. Yeah, I've spent way too much time on this game. But yeah. Oh man, so my contribution to this speedrun is the guy that the wheelchair guy that you have to shoot and he worms off screen. If you despawn his dead body off the left side of the screen, it saves you 10 seconds per kill. And that's my contribution to this game. And what I did is I played it over and over again, and I graphed the time it took him to respawn, and I found out what made that respawn time bimodal. So I used a scientific method to actually figure out this stupid game. We all have our hobbies, Sachin.
What's your favorite textbook? Like, what's the textbook that's felt effortless? You know, like the textbook I'm reading right now is a textbook like that.
I don't know about textbooks that I've fallen in love with. There's a lot of casual reading books like, I don't know if you've heard of Disappearing Spoon or Napoleon's Buttons. They're very popular chemistry books that are like casual, like talking about things like gunpowder and TNT. And
oh, okay, but like
things like that.
They're not chemistry. They're popular chemistry books.
Yeah, exactly. I don't know about textbooks that I've really fallen in love with.
I had 2 or 3 like that.
What's my Nick Turo's book? So the one that I make my students read when they first join the group is this one. It's called Modern Molecular Photochemistry. And it's really this foundational, like, what is a transition? How do you get from a ground state to an excited state? How do you describe, you know, the different transitions that can happen?
Like, what do you think? What makes it like?
It's just this really like cradle to grave. Start from the foundations, build up later chapters, gets into specific nuance of various different systems. And it was just like even if you don't know chemistry, this is a starting point for you to talk about these photochemical processes. Yeah, this is from Nick Turo, who is an icon in the photochemical community. Misadventures in Astro. Probably could have just decompiled the code. So my brother is a computer and electrical engineer, and he started reverse engineering this game through looking at the code, but it's non-trivial. This game is hundreds of times larger than Super Mario Brothers, so...
Oh, is it really?
Yeah, it's
wow, it doesn't look like that.
Well, Super Mario Brothers has very little, like, random number generation. Like, it's all predictive for the most part. It's a very specific sequence. In fact, you can predict what the last Bowser is going to do based on when you start the game and when you get to him.
Wow.
And so this one is much more random, and we don't know what predicts a lot of these things.
Okay.
So a couple additional inputs changes everything. And if you get sick of playing, I'm happy to take this hat out.
Okay, I'll do.
It's up to you. You have 8 minutes left before it's 11 o'clock, so you have plenty of time to play around.
Okay.
Added to wish list. Let's do it. Modern molecular photochemistry misadventures. It's actually pretty good. I really enjoy how it talks about molecules and the light matter interaction. So yeah. And as far as I know, all the games at the time were done completely in assembly. I mean, programming this, like it's ridiculous.
I mean, Nintendo's kind of good at that, right? The games don't look particularly like the game plays. Okay, can I?
Yeah, I'll take care of the hat. So, just got to get a little bit away. We'll see if I can do this first try. I haven't done it in a while. So it's literally a light tap, but you got to get it right in the hat. I'll get this. All right, so now the bullet guy. So what you're going to want to do is go between these two lines right here. Basically shoot bullets at him. Back and forth like that over and over again. I'll get you a little bit away. There you go. I paused it. So you can unpause.
By pressing start? No.
Yep, press start. Keep pressing left. So you're going to turn back, hold A button, shoot bullets. Because bullets are going to kill the vertebrae. There's two. So you're going to keep doing that, staying between these two lines right here. Go down.
Oh.
It's because this hitbox doesn't make sense unless you're down here. Those of you that have never seen this game before, I know way more about this than any human being should. I refuse to not get the record in this game. Wow. The original Pokemon games were all done in assembly, including turning the toggles and the pixels on the screen into specific positions to draw the sprites. Man, what a nightmare.
I know.
So Eugene, when he taught his programming class this semester, he actually made one of his assignments to program a game of some sort.
Oh, is that right?
Like Tetris or Snake or what? I mean, it's a fun way to do it. Like students are invested.
Yeah.
It's not necessarily.
So one of my colleagues used to teach a class in game design for the longest time.
Is that Chris Mills?
No, Gordon Orbacher.
Oh, okay.
And people made like pretty decent video games. You know, like, so I mean, like this. I mean, I don't know much about games, as you can tell, but
just move up and down just a little bit. There you go. Boom, done. Go right. There we go. Sorry. Yeah.
But you know, like you build a story, you have to have like a narrative.
Yeah.
Go there first.
Yep. Now you're on to civil forfeiture of the level. All right, go right. You're gonna find the door. If you guys have people we should raid, put them in chat right now. We'll raid them after we're done with the stream. But Sachin has just won the war on drugs. So you helped Biden decriminalize or declassify or lower the classification. All right.
All right. So this was 84. This is like
2517. Okay, so this is 1988. Yeah.
So this is like 95th percentile.
People that
are right. I don't know. Like you can't do more than 30. You said right? The game times that at 30.
No. You can do more than 30. I think your old time was like 30.
If you didn't pick up the controls for the big guy, then
next time though.
Is there a world record for the slowest?
I think the slowest is like 42 minutes or something like that.
Oh, is that right?
You're doing fine. You're on the schedule.
Wow.
We raid my friend. TJ, let me see. Yeah, we'll take a look. What are they streaming? I better ask that first before we start raiding random people. But Sachin, you can put your initials in there because you might as well. You earned it. That's the worst part. Is like after a long night of video gaming and streaming, I force my guests to play this terrible game, and after all that, after 3 hours of under the lights, plus drinking, plus answering science questions while video gaming, they have to beat that stupid boss at the end.
Yeah, cool.
Contra, thank you for staying by. Thank you for all the comments and suggestions. We appreciate it. The discussion has been it's been a lot of fun. It's taken us down many different interesting channels. We got to talk about polymers and soft materials and rheology and all sorts of different stuff. Computer programming, different programming languages. It has been a heck of a journey. But yeah, it's been a pleasure. Sachin, any parting words for the audience?
Oh no, this has been a lot of fun. I realize I just don't multitask well. I mean, I tell my students that they should switch off their screens when, during classes, and I feel like I should send a link of this video to them, just so they know how bad people can be at multitasking.
I don't know. I think Big Bumpin went well, right? That was
yeah.
All right. Well, everyone, thank you for joining us. It's been a pleasure. We always enjoy it. The questions are great. Join us again in 2 weeks. So May 15th, we'll have Dr. Brian. How do you say his last name?
Quaife.
Brian Quaife. He's also in scientific computing, but he does macro modeling, particularly fluid dynamics, and how that relates to, I guess he models fire and propagation, prescribed burns, and how wind and things like that affect it. So we got another theorist, third one in a row, but doing a very different level of abstraction. So we went from, Hitesh doing like electronic systems and physics modeling of solid state condensed matter, to Sachin doing much more soft materials, doing molecular dynamics and simulations, and Brian will do a much higher level that's applicable to.
He works with equations. He doesn't even see atoms. Just continues.
He does a high level abstraction. So stick around. We're gonna raid somebody. Let's check who's on. But ladies and gentlemen, it's always a pleasure. Thank you for joining us. We'll see you again in 2 weeks.